ahead. So tonight we're going to be doing probably the coolest part of anything that we've been doing up until this point. This is the week I always look forward to. But the problem is we need you guys need so much background to get to this week that we can't just dive right in because I just dive right into this if we could week one. But you guys need a lot of background to make that fair. So, um, but yeah, so it's gonna be a good time tonight. We are going to it's what are we are on week 11, so we only got one more week next week. We're not going to do any coding next week. It's all going to be more discussion, conversation. I'll do some advanced deployment stuff. We'll do some case studies, real things that real systems. Now that you know all the terminology and everything, and you can ask questions on that. We'll have a conversation about stuff, and then JC and I will give our best practices and those types of things, suggestions moving forward, and what happens after next week. But this week is it's this week you'll see it's a culmination of the entire 11 or 10 or 11 weeks that we've done so far, because we're going to touch every single point in the stack, because in order to really what we call operationalize machine learning, you have to. And so that's really what we're doing here. So you have now graduated from being an average software developer in knowledge and skills to now being a systems engineer, in my opinion, because the minute that you start actually doing optimization in the cloud is when you really start to shine in the context of actually having a really sufficient engineering background. It's That's really where we start to really break away from the average, software engineer, software developer, because of our ability and background to conceptualize systems, feature engineering, and really understand the plant, right, that we're concerned about. So, anyways, that's what we this week is. So, yeah, pretty much hang on. We're gonna go for quite a. It's gonna be a lot of stuff here, but we should get it done. If we don't get it done, like deployment, we'll probably do that on Tuesday. But a deployment's very easy. We're not missing anything if we don't get to deployment, because really it's just wrapping a microservice in Docker, which you guys have done before. So there's nothing crazy there. We will be, which I think you'll like, doing a REST API server in Python also. So we'll see kind of the combination between Node, which we've been working in, and then Python. I think you guys will like the Python. It's a little bit more comfortable. The reason we don't jump into it initially is because, well, as you saw, JavaScript just through the whole stack. And having that forced asynchronous type of thing is a very valuable thing, right? So, but we'll build it in Python. All right, show this here. So we are going to get started here. Let me share my screen. All right, so we've got lots of good stuff here. So I've only got 5 slides here, but I need to frame the problem because we're going to be doing some optimization. So I like to call this, and I've heard this in the industry a little bit, but I really took to liking this when I heard it for the first time. But the description of operationalizing machine learning, a lot of times when data scientists go and they build models and stuff, that's a pretty easy task. I mean, it's easy to do it from a textbook perspective. Read a tutorial and a few lines of code, you can have a full-fledged optimization implementation. But where the real challenge comes is in the operationalization of that. Meaning, how do I actually deploy a machine learned model? Once I have a trained model, trained optimization model, how do I actually operationalize it within the context of my larger ecosystem? Because what's the point in doing it if you can't use it, right? So that's what I mean by when I say operationalization of optimization. Moving out of the classroom, moving out of the university and into the real world of actually doing something with it. So before we go crazy, We'll take a little bit of a background here on what optimization is. I hope all of you have had optimization at one point in your classes, whether it's undergraduate or graduate school in engineering. Clayton, you may be the only one that has never had a class in optimization.
Oh,
But
we do that in linguistics all the
I,
time.
I figured you did in
Yeah,
computational
it's a big
linguistics.
linguistics thing,
Yeah,
right?
that's a huge thing. So um, Clayton may actually be more well versed in the theory of optimization than some of you might be. um, but really, what is optimization, right? So straight from Wikipedia, it's the selection of the best element based on some criterion from the set of variable alternatives, right? It's just what's the best answer. That's what those pretty words say. So what this means to us as engineers and mathematicians and all of that kind of good stuff, where people have to implement this, is we have to define a real function. Of course, real is being used there very specifically. A model, and maximizing or minimizing the output of that function. You can think of it as a black box in our context. By systematically choosing input values. Those input values, you hear me call them features or feature engineering. Um, and that's in the context of machine learning. Within an allowed set and computing the value of that function with those inputs. So, pretty straightforward. But really, what it comes down to is we are looking to define some sort of real world thing and create a little black box that we can put inputs in and get an answer out. And that answer out better be the optimal, right? The best answer, or as close to as we can get based on our given training data. And so, what are two forms of basic models? And we can argue about this forever. What this actually is. I think there's probably more like 25 or 26 official ones. If you go to like a textbook of what that. But in my world, I basically look at two different types of models in optimization. The first one is what we're all familiar with and what we've done in school since the very beginning. You guys probably do it in jobs too if you're practicing engineers. And those are dynamic system models, right? Physics based. That's where we take physics and first principle models, first principle elements, right? And what we do is we define a mathematical representation of the real world using some sort of physics based, and then we identify those parameters, right? Optimization, to match whatever our data is. That's what we as engineers, particularly academic engineers, do most of our time. Quite frankly, mathematicians do this too. And then the other are what I like to call data driven models. And these are most predominantly stochastic models, statistics, right? Based in statistics, heuristics. Examples of these would be like social sentiment, human behavior, the things that are so complex in terms of the number of variables that they are physically impossible to mathematically model accurately to even get something in the ballpark, right? Clayton, as a linguist, knows that language is one of those really difficult problems, right? It is so many, there's just so many variables that go into how we speak, right? And the meanings and the context and the nuance and everything. It's just too hard to come up with some physics based thing to say, oh, yeah, that is the rule, unless you're a robot or something, right? So, from that perspective, those are the two forms. And so I'm going to focus on that today on that last one, stochastic models. Number one, because I like it the most. I'm a computer scientist, right? So I tend to gravitate towards those things. I've degrees in mechanical engineering, so I've done my fair share of physics model. In fact, my entire thesis was on a Thevenin equivalent circuit model for a battery, right? And so I tend to gravitate towards machine learning because one, it's there's a lot of money in it because of buzzwords and everything. But two, I tend to like the ability to be able to represent things that are exceptionally complex in a very simple form, very simple and elegant way. I also like the plug and play ability of machine learning, and you're going to see this when we build our model. They're generally easier. It's another reason why I like them. They're generally easier. The basic rule of thumb is if you have enough data, and that's the basic rule of thumb there, that's always the hardest. The tools that exist, you can make pretty good models, and they're pretty plug and play. All right, so in our case, let's pick a machine learning model. For those of you, you've all heard of machine learning, right? It's the biggest buzzword nowadays. AI, right? What's the difference between AI and machine learning? There's a bunch of different explanations for that, and we could go on hours talking about what the differentiation is and all that kind of stuff. I don't like the word AI. I think it's too much of a buzzword. Not to mention that when you say AI to me, I think that's sentience, right? Something has to have sentience in order to be artificially intelligent. Well, we haven't done that yet and won't for a while. So let's just stick with machine learning because that's actually more accurate when we call it that, right? So there's a billion and one different machine learning optimization methods that you can pick out of a toolbox. We're going to pick one tonight, and that's called random forest. We're not going to attack a neural network. That's the more of the popular thing. And when you say AI, people tend to gravitate towards neural networks. We're not going to use neural networks because you need a massive amount of data to even get close to a right answer. We're not going to do that tonight. We're going to start with a simple example. And random forests are really good when you have smaller amounts of data, and they're relatively easy to understand. If you look at the two pictures over there, um, these things are rooted in decision trees, and we all know what decision trees are, right? You simply just go down a tree, and then you take a route on the leaves, depending on what your condition is, right? However your condition is satisfied. And so the thing about a random forest is it's just a collection of decision trees. And these decision trees are what we say bagged, or they're classified based on certain things with the data. And there's basic rules within random forest algorithms that basically define these classes for you when you go to train it. And it's all based on heuristic statistics and things like that. It's what we call bagging. And so on the prediction, these classes, which are just, you can think of as multiple different decision trees, they're all queried, and the best performing one, based on an error, is the one that's chosen to give you your prediction. So you can imagine that's pretty robust, right? And they're pretty good. In fact, I would dare to say that if someone comes to you and says, "Yeah, I have a machine learned model," I'm not going to tell you what it is, but I have a machine learned model that predicts something really well. I can almost guarantee it's a random forest. It's kind of the go-to thing if you're just looking to put something quick together. Use a random forest because you're probably going to get a really good answer. All right, so what is our problem? Well, our problem is we have this really nice model, right, of Sumo. We've been doing automotive, and this is a pretty typical AV, autonomous vehicle problem. And that is we want to predict trip time of our EV, of our electric vehicle, based on weather and time of day. Now you might say, well, Google does this. How well does it do it? Kind of whatever, right? Sometimes it's good. Most of the time it's bad. Um, but this is actually a pretty difficult problem, right? Because one, in order to do this from a dynamic systems perspective, you would have to have physics-based models of the weather. Good luck, right? And then you would also have to somehow model volume and demand of the traffic during that time. So you'd have to have some sort of sensor data and all those types of things, which is somewhat difficult to do, as you can imagine, right? Because there's a lot of things that impact it. So there's a lot of features, what we call features, right? So what I'm describing here are features, weather, and there's a lot of things in weather, right? It's not just, oh, I have a number of weather, and that's my number. We can't just feed a number in and say that's weather. We're gonna have to think about our features of the weather, and then the time of day. Well, if you want to do it at a second basis, that might be a little bit too crazy, right? So we're going to do something called feature engineering, and I've already kind of done it for you here. You can look at the slide. Really, feature engineering is really where the art is in machine learning. It all comes down to your features. Because these are such plug-and-play models, like random forest we're going to use, it really comes down, the quality of your model comes down to how good your features are. Now, we're not going to go over things like principal component analysis and all the different things that go into supervised and unsupervised learning in order to identify your features. We're just going to assume that we've done all of that analysis and sensitivity stuff and come up with features. Spoiler alert, guys, feature engineering, it's just a lot of trial and error. There are certain tools you can use like PCA, principal component analysis, and k-means clustering and things like that to try to cluster and find things, but when it comes right down to it, you're still just trial and erroring to find your best features. So our features, because they happen to be good for the model that I built, is humidity. So we did two features out of weather. humidity, basically if it's raining or not, but we're going to use that as a percentage because it does impact, as it turns out, uh, the level of humidity, even if it's not raining, people tend to drive differently. And from a PCA perspective, principal component perspective, that tends to impact people's ability to drive well, which impacts traffic, right? Even if it's a little overcast, that actually does impact. May not be raining, but overcast does impact travel times. The temperature. Now you might say, well, how does temperature impact? Well, if it's really cold, it does, because that combined with humidity, that means ice potentially, right? So that also has an impact. And then hour of day. Now, why didn't I do second or minute? Well, because we don't have enough data, and quite frankly, trying to do something like that to try to predict on a minute by minute basis, that'd be crazy. So we're going to bucket. We're going to actually more classify this to just say 6 a.m., 7 a.m., 8 a.m., and we're going to do that. So here's the question for you guys. What should we actually predict for our output? It's actually the hardest part of machine learning. Is actually figuring out what your output is.
Average vehicle speed?
We could do average vehicle speed. That's going to be pretty tough because average vehicle speed is that's a lot of possible answers in that.
Elapsed time.
Elapsed time, that could be all over the place because
Since
if you think about elapsed time, which is the obvious one, right? Elapsed time, it's geez, well, that could be anywhere from an hour, 6 hours. It could be 3 seconds. What's the length of the? And if you notice, one of our features isn't trip length or distance, right? So that could be anything. So that's going to be way too big of a problem to try to get any accuracy on. So
You could
So-
work on variation from the norm.
you could do variation.
How far off would it be from the normal trip?
Exactly. We're getting closer. So I'll give you the answer. How about a severity factor? It actually is along the lines of what Clayton was saying. It's a severity factor. So the variation, basically the impact of what it is from your ideal trip, right? And as long as you know what your ideal trip is, which, oh, by the way, we do because we can model that, then what we can do is we can apply a severity to it. And the beauty of severity is you can basically have any number of answers that you want. You can have a low, medium, high. You can have a, 1, 2, 3. You can have any kind of classes. In our case, let's do a 0 to 100%. So there's a lot of classes to predict, but there's actually exactly 100 classes to predict. But I think that's okay because that's going to give you enough resolution. And since we're already losing a lot of resolution in the hour in the day, because 8:30 may actually be different than 8:45, right? We don't really feed that in. We're only feeding the hour. The severity factor is going to give us, and we're going to actually be able to capture a little bit more with maybe demanding a bit higher resolution on the output as opposed to trying to put that in on the input. So that's what we're going to go there. And so we're going to do a severity factor. We're going to do that based on that ideal trip. And as it turns out, what I said before is we're going to need model in the loop to do this. And this is where this gets even cooler. Because now, not only are we going to combine a machine learned predictor, but we also have to run a model along with it because we need to actually predict what the ideal trip is, which we can do from a model-based perspective because models, well, one, they always lie. Models lie. That's the number. There's death, taxes, and models lie. Those are the three things that you can guarantee in life. And that model, though, we don't care if it lies because what we want is that ideal trip, right? And as long as that ideal trip, meaning no traffic, no weather, it's just perfect conditions, we can model that because that's what models are really good at. So if we can run that really quickly, what we can do is we can then predict the severity factor, put those two things together, and get the actual trip time, right? So we're going to do that tonight in our system. So let's do that. All right, any questions before we go crazy?
Yeah. I just have one question. You said that you have this factor of 1 to 100, and you say I'm going to do a severity of it, but that we're going to do it basically by hour. Would you then model it where you do a average over that hour? and just say I'm going to pick that each hour is going to have the same severity?
Yeah, so that would go into more of the sensor. So how do you actually collect your data? So that actually leads into my next thing here is let's look at the data that we have. So I generated some data, fake data, of course. And this, there's not that much. There's not that many. There's only 39 observations. It's pretty awful. But we're using a random forest, so it's pretty robust to that. And in fact, I only model 3 hours, 7, 8, and 9, or 6, 7, and 8. Maybe there's a 5 a.m. in there too. So I'm doing it on a 24 hour, so it's just integers, right? Thing about machine learning, got to convert everything to at least a real number, right? So what we're going to do here is basically this data is only about 4 hours, so good luck, right? Trying to get anything beyond that. In fact, but I guarantee that it will not, because we're actually going to use a random forest regression, not a classifier. And that regression, which should be a little bit more familiar to people, similar to a linear regression, as I'm sure some of you, a lot of you, most of you have done in the past. The regression cannot extrapolate, particularly random forest regression, cannot extrapolate. And so we're at least going to either get the max or the min if you're trying to go outside of those bounds. You can always generate more data, right, just based on some rules and some randomness. But this tends to work okay. And so we've got our features, our humidity. So let's say we collected that from some sort of weather API or something like that, historical weather API. We collected the temperature, also easy to get based on weather APIs. You got your hour, which you could say, okay, the hour is 6, 7, 8, or 9. So to your point, Beth Ann, you could say it's an average or whatever, but I'm just going to say if you're within that, we're just going to round it to the nearest hour, right? Ceiling or floor, take your pick. And then trip factor multiplier. Well, how do you get the trip factor multiplier? Well, that's relatively straightforward because we can run our ideal model like Sumo. And then what we can do is once we run our ideal model, we can say, all right, how long did the trip actually take? It's a simple timekeeping thing, right? Start a stopwatch for a vehicle, you take your trip to work, you sit in traffic and you say, well, when I ran the model, it should have been 50 minutes. And when I actually ended, it was actually 61 minutes. So there's your time, right? 11-minute difference. That's your severity factor. Take the ratio of that, then you get your fraction. And this is between 0 and 1, or 0 to 100%. That's basically what you can get, right? Now that's somewhat limiting if you think about it, because what happens if you have 1,000% or whatever? Well, that's okay, because as it turns out, that's not necessarily limiting. It's really just depends on how you define it. In our case, we're only defining it as the maximum overage time is double what the typical ideal time is. But that's just how we model it. See, it always comes down to the amount of data that you have and how you define your problem. So in this case, we've just defined our simple problem in order to get it done tonight. But as you can imagine, you can also add a lot more features. There's a lot more things that impact this. And I challenge you to think about it. These are kind of fun problems to do it. And the art and the experience comes into thinking about these things. Now, how did I know to do a severity factor as opposed to like a trip time or something? That's pure experience. If you do enough of these, you end up getting an intuition for how you define your problem, your optimization problem. And it is truly experience. You're not going to come out of the gate doing it. After we're done tonight, you guys are all going to go out and I can almost promise you're going to be like, man, I can predict the world with this. And it's true, you can with enough data. But you'll get into it and very quickly you realize, oh crap, you pick your problem and everything. It's like, oh crap, what should my output be? That's number one. And two, what should my features be? And that's really where the art is in matching your feature definitions with your outputs. And that's where the intuition comes. And that intuition is also based on the actual machine learned model you choose to. So anyways, we got this data, pretty straightforward. Let's go over a few examples here. So it's raining here, so we have a 1, right? So it's 100% humidity. It's 25 degrees Celsius, and we're at 6 a.m. and you get about a 34% increase in travel time from the ideal, right? That variability. If you take one in the middle here, Let's see. This is humidity, so it's not raining. It's only 30% humidity, so that's pretty solid. It's -5 degrees though, so it's pretty cold. And it's 6 a.m. And so I guess when it's cold, people tend to drive a little bit slower. Only an 11% increase in from the ideal trip time. Now you might also say, all right, well, that's fine, but that there is a significant amount of data that I would need to do this. So even in our simple problem, it's almost too contrived, particularly from even a sumo perspective. Because what we're saying is this model is supposed to predict going from maybe your house to a job maybe 20 miles away. But then it's supposed to work for you going 5 miles away or even just down the street. No way. That's never going to work. In an autonomous vehicle, we don't do that either. What we do is we actually section it out. We split it up. The reason is actually more impactful, and we'll start to see this with the IoT. We're actually going to do it by a traffic area zone, a TAZ. So you'll hear me talk about a TAZ a lot. And so what we're actually going to say is this machine learned model, this specific data, is actually we're going to have an additional feature, and that additional feature is actually implied here because we're only going to train a model for the specific TAZ. That feature is the traffic area zone. Now, traffic area zones, if you don't know, they're defined by regional planning commissions. Every state has certain areas that are traffic zones. They're pretty small, a mile to a couple miles wide or something along those lines. They're actually used quite frequently in planning, urban planning, and things like that. So if we have a bunch of different, so let's say we take every TAZ in the entire United States, which would be in the order of hundreds of thousands probably, if not more. What we would have is then at that point, we can actually have a trained model for every single one of those TAZs. And that's what we're going to focus on today. So the maximum time, if you can think about it, from a TAZ entry to a TAZ exit is probably on the order of minutes to seconds. So you're really not worried about predicting really long time. And in fact, that is a very impactful thing, right? Because if you think about it, if you predict when you're starting your trip and your trip is an hour long or even 25 minutes long, you think that at minute 19, something's not going to change, your prediction is going to be off, right? Because it's too chaotic. So it's actually safer to predict in chunks. So only do a look ahead in very, very short increments. Not to mention the fact the amount of data and the amount of processing power goes way down if you're doing that in chunks, right? Which is what we actually need because we have to run a model in real time for every single trip. So that's actually very critical. Now we're going to see that in a little bit. All right, so here's our data. That's cool. So I've already pulled this. I've already pulled down our week 11 here, and or changed week 10 to week 11. And you'll notice what we're going to do is architecturally, if you think about it, what do we have? We've got our gateway or our cloud, right? We got our embedded domain, which is our vehicle. We have our client domain. We have our databases. We have our broker. But we have a concept of a microservice now. So if you think about it, we could, in theory, we could build our prediction into our cloud as a route handler, right? Because our vehicles or our client side could actually hit our back end, right? And it could say, all right, that's cool. Hit the route, do the prediction, send me the answer back. And it could all be in one cloud system, in one code base, basically our cloud. I'll give you an example here of that. Here's our index.js, right? This is our cloud. You should be pretty familiar with this by now. Okay, so we've got all of that. And we've got, we could just create a whole new route that's predicted, and do all the stuff in there. Now that's pretty limiting. Why is that limiting? Anybody? Anybody?
Been used.
What's that?
Um, ports, availability of the ports.
Nah, not so much. I mean, it's just another route, right? The reason that we that it's so it's not a great option is because you'd have to do machine learning in JavaScript. Who the hell wants to do that, right? There's no libraries for it. Well, there are TensorJS stuff, crap like that. You don't want to do numerical computing in JavaScript. No, you just don't want to do it. So what that means is that we need a way to leverage things like Python, because there's a massive community, tons and tons of libraries for machine learning, very numerically friendly. We need to be able to use Python to do these predictions. So now what we're talking about are APIs, right? So let's think about that. Let's make another cloud, right? Another REST API that its only job is to do predictions. So if we define a contract, let's say between our cloud and what we'll call this microservice, this prediction microservice, because that's all it is, right? It's a service, just like our cloud is, but it's a microservice. It has one function, one job, and that is to do predictions. But the beauty of it is that you can basically isolate the functionality in this microservice, right, to do certain things that it's really good at, and then provide the answers back to your general purpose thing, your cloud, your JavaScript, your Node backend, or what we call a gateway. Because if you notice, I'm going to start calling our cloud a gateway, because that's what it is. It's now a gateway to microservices, and possibly doing some work itself. But it really becomes a gateway. And so the cloud will just broker through predictions and things like that and keep a uniform, consistent API with our clients and our embedded domain. But at the same time, it will also communicate via an API to this new REST API. So in the beginning of class, I said that we would be developing a REST API in Python. Well, we're going to have to do that because the only way to define a machine learning API or a microservice API with machine learning, we have to do it in Python. We're going to use something called fast API. But before we do that and go crazy with that stuff, let's just do some modeling first. So I'm going to create. So I've got a week 11 folder. I'm going to create a new folder here. I'm going to call it trip prediction microservice. And in here, I'm going to create a new folder, and I'm just going to call it model dev. We're not ready to define that REST API and everything yet. We're just going to, this is where we're going to build our machine learned model before we do all of the infrastructure and everything. Because we have to actually, validate and verify that we can do this correctly. All right, so we got model dev, and I'm going to put a new file here. I'm going to call it train.py. And I'm going to, so if I'm in here, I am going to copy the file that we looked at, our data, to our week 11. All right. And then I'm going to go into our week 11. I'm going to do our trip prediction microservice. All right. But then, and then I'm going to create a virtual environment in here. Well, actually, yeah, I'll create a virtual environment in here. And then I'm going to install a few packages here. So we now look at our trip prediction microservice. We've got our trip times, which is our data, right? Training data. We have our train.py, which is going to be where we build our model and train it. And then we'll have a predict.py, where we can just run we can do our testing there and stuff too. All right, so in train.py, we've got a few libraries we got to do. We got to pip source vn bin activates. So we've activated our virtual environment in there. Now we're going to pip install a number of different things. One of those is Pandas. Pandas is a really nice data manipulation library. And then we're going to install NumPy. NumPy is basically linpack and everything in Python. So MATLAB and Python. So if you do any Python, any numerical stuff, you're going to want to use NumPy. And then we're going to use sklearn. Sklearn is basically a really nice, it's the foundation of all the machine learning that we do in Python. So it's got a ton of really great models and all that kind of good stuff in it. And then, so we got all of those. So we're going to install all those in our virtual environment. And then up here, let's start to import these. So we're going to import Pandas as PD. And we're going to import NumPy as NP. And then we're going to do sklearn dot model selection. And we're going to import a few helper things, train, test, split, and I'll explain some of these as I actually implement them. And the sklearn dot pre processing. I'm going to get a standard scaler. There's some details here that we'll go over. And then from sklearn, we have to also import ensemble. And then this is actually where our random forest regressor comes from. And it's that easy. That's why a lot of people do machine learning. These things are just basically packaged up for you. And then a few other things, sklearn, we're going to import some metrics so we can do some classification reporting. And then I'm also going to import pickle so that we can export the model once we have it. And then we'll be able to, I'll be able to dump it. And once I export the model, we can import it then into our REST API and use it. So we can train it, save it, and then import it when we need it. All right, so looks like that stuff's loaded up. All right, so we have to let's load up our data set first. So we're gonna have to import all of that this triptime.csv. So data set's gonna be equal to pandas, and pandas provides us a really nice function called readCSV. So it's really nice. Triptimes.csv. If you've ever done any importing CSV into any programming language, it's a pain in the ass. Well, Pandas makes a lot of that easier. Datasets.head. So we're basically just going to start at the top there. And then what we have to do is we have to format some of our inputs. Now, without going into too many details on the standards of things, typically you have X's and Y's, right? X being the inputs to your model, Y's being the outputs. We're gonna keep that convention for our variable naming here. So we're gonna say a capital X, and we're gonna say our data set it's a pandas data frame. So we're gonna say, all right, if we look at this, here's a matrix, right? This is just a matrix of numbers, right? It's a 4 by whatever 38 without the header. And so what we actually want these 3, 0, 1, 2, and 3, right? We need those to be our inputs, and we need that last column to be our output. So all I'm going to be doing here is I'm just going to be doing that. So I've got the rows and the columns. So 0 through 3 is my X, and then my Y is dataset.I locale 3. So that's my Y, and I'm just need to get the values off of them. All right, and then basically we're going to say, all right, X train, X test, and Y train, and Y test. Now, what is X train and X test, and then Y train and Y test? Well, what we can do is we can use this library that or this function that I imported, and I'm going to say train test split. And what I can do is I can say, all right, typically in a machine learn type scenario, what you want to do is you want to, of all of your data, you want to split it up into a training set and a validation set. You don't want to necessarily train on all your data, right? You only want to train on a certain amount of data. And so what you end up doing is where you can do like a 60-40 split or a 70-30 split, where 70% is training data and 30% is validation data. And what this function is doing, I think it's 70-30 is the default. What S is doing is it's taking my my X and my input data, my output data, and I'm saying my test size, let's just say, let's do 80-20 actually, so 0.2. So my test size is 20% of the data, and then I'm just going to say my random state is 0. So you can kind of initialize that as random. And so all we're saying here is that I want 20% of my X and Y. So 20% of these, whatever that is, like this chunk will be test data, or will be validation data, as opposed to test data, right? Because you don't want to train on everything and then validate against your training data, because you're going to get the right answer, right? So you want to make sure your model works. So we're going to do that. And so we've got that, and then there's some other things that make it a little bit more difficult than just using your data. You got to scale your data. So we're gonna.
Quick question for you, BJ.
Sure.
What's the largest percentage you've ever seen for somebody using for their train set?
Maybe 30%. Maybe 30. Why?
Just curious on like how much somebody's pushed the boundaries on that one.
Yeah,
in terms of what's considered acceptable.
Probably 30 is the most that you want to go. It really depends on the size of your data, right? Like we don't have a lot of data, so doing 20% is pretty generous. You should probably do more like 5%, but even then, do you really get a good validation? Because what we're going for is to do some squared error stuff, right? We need to do some. We need to make sure that the error is okay. So if you only have like one sample to test against, well, how good is your error metrics going to be? So
what we typically tell students, or when we're doing it in statistical modeling, is that ideally you would use half and half. Ideally you would, but it depends on how much data you have. You have to have enough data to be able to comfortably do that. The other thing you want to do is randomize it. That at least we have found is that you don't want to pull it all from one section of the data. You actually want to intersperse it. But that's just practice within statistics.
Actually, what this train test split does is it will randomly select. It won't say, oh, just that what I said, like this is just an example. It does actually do a random selection. And in fact, the random selection with initialization random state is 0 in that case. So that's what this random state is. Yeah, exactly. Well, half and half. Yeah, statistics, I guess, is half and half. I don't know. In machine learning, you really want to train on as much data as possible. So you typically will go, as small as possible. But you can't go too small, right? In terms
you don't just increase the training percentage until your validation comes into where you want it to?
Well, if you want to fudge your data, yes. Now, in graduate school, that's what you do in order to get your dissertation. But when you actually, have to do something in real life, yeah, then you're doing what we're doing here.
Okay, speaking as the faculty, we know when you do that, and we're going to ding you when you do it. But you're right but the problem becomes that you don't know if your model is correct then.
Right.
Like you can make it correct, and that's maybe what they're all doing in machine learning. That's why the models are so good.
Oh yeah, that is exactly why they're so good.
I don't know. We can identify cats really well.
That is true. We can identify cats really well. There's a lot of cats on social media, which is probably why. So we've got, see, it's all about data size, right? The other thing about machine learning, or statistics, but especially machine learning, is you have to scale stuff, right? You have to normalize everything, because it's all about linear algebra. That's all machine learning is. Just different fun. It's fun with linear algebra. So what we have here is a couple lines that we're going to use a standard scalar. there's a ton of different scalars depending on what your data is, and it all comes back to your statistics, right? With what kind of scaling you want to do and how you want to weight things. What we're trying to do is we're trying to fit the transform, and then once we fit that transform, we need to actually transform it for that test. So we're just doing some scaling and then transforming it into a usable format. So we're just playing with the matrix sizes and stuff a little bit, and then we're scaling it to normalize all the data, probably between 0 and 1, although I'd have to look into specifically what the implementations of these fit transforms would be. All right, and then what happens, the magic here is we now want to identify, right? This is our parameter identification stage. So first we need to make a regressor, and we're going to use the random forest regressor. That's how easy this thing is. So the number of estimators, trees, right? We're going to say what's 20. The random state, we'll just say 0 again, make it easy. And then the real magic here, there's a function on this regressor called fit. And you just pass your X train and your Y train, which is your answers, right? And then you've basically got your Y prediction, and you can say regressor dot predict, and we want to predict against our test set, and that is machine learning, guys. It is that. It's sadly easy, because then it's so plug and play. So when I say plug and play, it is truly this easy. If you wanted to use a like a, I don't know, a convolution neural network, or an MPC, multi-perceptual, a neural network, a DNN, something along those lines, you would just import that from model selection, and you just replace this right here. The API is the exact same, because that is why machine learning is so popular and so powerful too, because it's more about how you do, and that's also why I'm stressing it's all about how you do your feature engineering, because they're all very standard formats, but it's all about how your features match up with the math of your selected optimization problem out of your toolbox and what you're trying to predict, because the formats are all very consistent. And that's also why when we Justin and I go to a client and they want us to do some machine learning and some optimization, we always say, yeah, well, we're gonna budget so we have time to try 3 or 4 different model forms, because it's really easy to do, but you have to do what we call hyperparameter tuning. So that means maybe playing with this number of estimators, and every single one of these different machine learned models have different hyperparameters. That's where they start varying. So that's where you have to read a lot. You have to understand the math behind it and all those things. But generally, the defaults, you can just attack problems with defaults, see which ones tend to give you the best thing with your current data, and then you start honing those or doing hyperparameter tuning. All right, so we've got that prediction. So let's do some stuff here. Let's look at printing one of the. Let's do an absolute error. So mean absolute error, and we're going to use this regressor dot predict. Oops, I'm sorry, not yet. Let's just do it. Let's use this metrics here. Dot mean absolute error, which will compute it for you. We're going to do Y test against Y prediction, right? Because we want to compare our test against our prediction. And let's see how that works. All right, so let's Python, let's see, cd model dev. Let's just run python.train. Let's train it and see how it works. The mean absolute error is pretty good, because the error is closest to 0, right? Now, I'll make it seem like it's better than it is, but I did play with this for a while before we did this, so did tune this a bit to make that error pretty low. So it's not like we got lucky there, and that data was well formed because I made up that data to fit the random forest that we're using. So not quite as easy as it looks here, but generally that's pretty good. You can also do mean squared error and all of those different things, and they tend to give you about the same thing in terms of that. So that's pretty good. So let's predict a nice day. So we'll just do some sanity check stuff. We are engineers after all. So regressor dot predict. And we're going to predict a NumPy array. And we're going to put a NumPy array in of, let's see. I'm not going to go over that. You guys can watch this video again and figure that out. It should be relatively clear now what that means. So let's do, what are we trying to predict? Well, in terms of our matrix, our input features, we have what? Humidity, temperature, and what? What do we got? Humidity, temperature, and time of hour, right? So let's do a nice day. So let's say 0.4 humidity, right? 40% humidity. That's relatively, well, kind of low depending on where you are in the country. Let's do 16 degrees, so a pretty nice day, centigrade, and 7 a.m. So nice day, 7 a.m. Let's see what kind of prediction we've got. What that severity. I'd expect the severity is relatively low, and it is. Only a 6% increase, right? Still 7 a.m., so you're going to get a little bit of rush hour traffic, but it's still pretty good. Let's predict a really bad day. So what would a really bad day be? Well, it'd be raining. It would be, let's see, like -3 degrees, so right there at freezing, so really cold, so everyone's afraid of ice. And let's do it like 8 a.m., because our data says at 8 a.m. in this TAS that we're doing, 8 a.m. is probably the worst. So let's see how that works. We're actually training each time we do this. That's how fast this is. Wow, almost 50% increase in severity, which you'd imagine, right? About, add 50% time, right? On a bad traffic day. So, how cool is that? We have a prediction. We have a model that we can run really well and almost in real time. That was really fast, right? So that's pretty cool. We have a model we can run now to predict how much a trip time is at the beginning of a trip. So if you think about this, what if we wrapped this in a microservice, in a REST API, so that our cloud could then get the answer every time a vehicle entered a TAS? Or a client on their app could be like, hey, I want to predict a trip, like what you do every day when you, or well, pre-COVID, when you actually went places on Google Maps, right? So, oh, by the way, this is how kind of Google does this too, right? So this is what we could do is we need to export this model, because the one thing we don't want to do every time, right, is we don't want to train it every time. We only want to use the model. And the beauty of this, if you notice, we just did regressor and then regressor.fit, and from there, this regressor object has all that trained data in it. So it has those bags, it has those forests in it, already defined in memory. Okay, so, but we need to, what we call serialize it. We need to save it so that we don't have to retrain it every time. We could just import it when our microservice boots up, and it already kind of has all of those trained data in it. Well, it turns out sklearn gives us a really nice thing. In fact, Python gives us a really nice thing, not even sklearn. It gives us this thing called pickle. What pickle does is it serializes Python objects and data. And that's a really awesome thing, because it basically allows you to take a snapshot of your current runtime and then open it later. So you don't always have to be running it. So let's do that. So we do a with open. I'm going to open a file. I'm going to call this, let's see, trip time predictor. If I could spell trip time predictor, and I'll just call this, I'll do a random job lib. It's just a random file extension on the end. It's more convention than anything. And then as my file pointer, and so I'm doing that, and then I'm going to use dump, which comes from the pickle library. So this dump, it's just a function, and what dump does is it just serializes this regressor object into this file right here, joblib. So that's a little bit of Python for you. So let's run this, and we should notice that it'll create this file joblib over here. So now we have a serialized function, and we'll open it anyways. That's what our machine learned model looks like. It's just binary. But fortunately, Pickle or Python knows how to import that and make sense of it for us. There's some compression in there. Actually, you can see it. It's got some import stuff in there. It's got some threshold, yeah, weighted end samples. So that's some maybe attributes on it. Clayton, you might actually know better if you've done any Pickle work before. Some of the, you could, you know, if you read the spec for Pickle, you could figure this out and decode it. It's not like it's encrypted or anything. All right, so we got train, so we have this. So now what we have to do is we have to build a REST API to now house this predictor so that when a vehicle asks for a specific trip prediction time through a TAS, we can predict it and send it back. Right, so let's do that in this predict.py. So in here, I'm gonna say from Pickle again, because this is the other side, right? I need to load in that job file. So I'm gonna import a function called load. And then I'm gonna import NumPy again, because I'm, you know, I have to do that. I'm gonna have to import a few things, pathlib, and I'm gonna say path is equal to pathlib dot path here, whatever the current file name is for this, and I'm gonna get the parent of this, and gonna get the absolute absolute path of the current file. Don't worry about this so much right now. I'm doing this because we're going to need to move this thing around, and it's going to start impacting us when we start to do like Dockerizing things and everything, that we get the absolute path of this so that we're not constantly fighting with not being able to find files and stuff within the context. And I don't want to hard code the absolute path here, because you guys might want to download this and use it on your machine, and your machine's path can be different than my path. So we're just kind of abstracting that at this point. I'm going to say regressor is equal to none right now because we don't have it yet. But then I'm going to do the same thing that I did before. I'm going to say with open the path. Path here. And I'm going to say slash trip time predictor dot joblib. So I'm going to import that file that we saved that has our trained model in it. This time I want to read it as F, and I'm going to now assign that regressor. Now that we have to, that's outside of scope, I'm going to load in that from the file F. And from there, now I'm going to define a new function. I'm going to define it called predict. And I'm going to now abstract this a little bit. So for every humidity, for a humidity, temperature, and hour, I am going to define my input features. If you notice, those are my inputs, right? My input features. I'm going to say, all right, I'm going to convert this to a NumPy array so I can feed it into my machine learned model. And I'm going to say humidity, temperature, and hour. And I am going to then say, I'm going to return the prediction. So regressor dot predict of my input features. And as it turns out, this regressor dot predict, it can actually take a number of samples or input feature sets, tuples, and will predict it. So we actually need the first one off the top there because we're only predicting one. So basically the contract for this specific function is to only return one prediction, not multiple ones, because we're only inputting one. Humidity. There we go. All right. And then, just so that we can test this, we're doing a little bit of Python stuff here. I'm going to say if this function, if this file is run as the main file, then I want to run this code. Otherwise, don't run this code. Now this is important because what this allows us to do is also import this file as a module, but not run code in a specific way. So I'm going to kind of do some double duty stuff here, and I'm going to actually test this thing. So I'm going to say predict. I'm going to say humidity is equal to 0.4. I'm going to do that nice day example. Temperature is equal to 16. And I'm going to say the hour is equal to 7. And I'm going to say print prediction of trip time severity. And I'm going to say prediction. So what that allows us to do is Python predict.py, run it. Looks like I did something wrong. What did I do wrong? Anyone see what I did wrong there?
It's in the load function.
Oh,
So
Load
it's
binary.
not loading for some reason.
yeah, I have to load binary actually here.
Yeah.
So you know, remember this is all binary. It makes no sense. I can't read it as a regular file. I have to read it as a binary file. That's okay. So that should work. Right. So it does not work. Oh. I think I need to put this into a array. There it is. Prediction trip time severity of that. Now that little bug that you saw that I had in my code, that's just reading the documentation. That's one of the more frustrating things about this machine learning stuff is that it does take a very specific format in terms of, you know, your transpositions, your matrices and things like that. So you probably pull your hair out a little bit on it. If you do enough of these, you just get used to it because once you learn it, pretty much everything is like that in learn. And that's kind of taken to like TensorFlow and other machine learning libraries like that. So, yeah, all of this stuff is just reading the documentation. Predict happens to take an array as its first input, and then inside of that array is you know, an array of arrays. And these arrays, of course, are NumPy arrays that take your features and can do multiple predictions on multiple future predictions. All right, so we now have a nice little library, a nice little function called predict that takes our loaded model in, and now we can use that and build a REST API around it. So let's take it another level here. So let's go back out here and let's create a main.py. Right. All right. Who's heard of Fast API before? I hope Clayton has, because we've been doing a lot of Fast API lately. Justin, JC, you've heard of Fast API? Crazy.
Maybe.
The Fast API is like Express for Python. There's a lot of cool things about Fast API that Express doesn't even have. Still Python, but Fast API we've really gotten into in the as of late. We tend to what would we say, Justin? I think we do probably half and half, Node or Express and Fast API. Maybe a little bit more Express than Fast API, but we've been doing a lot of Fast API lately.
Yeah, and I'd say we get a little bit of ebb and flow depending upon what project we're on and what language we need it to be written in, right?
Yeah, if we do a project with a lot of machine learning or potential for, we'll use Fast API because it's in Python. If we're doing more of a standard kind of web app kind of thing, we'll probably use Express and then microservice like we're doing now. If we need high concurrent connections, like an IoT thing, JavaScript is pretty good at that. Node is really good. Python tends to struggle. You have to do a lot of tuning with Python to handle that many concurrent connections, which is why we've introduced Node first. and why we're building our IoT gateway in Node and not Python. Anyways, we've got Fast API is really amazing. It was made by this guy, Tiangolo. I think he's Spanish. I think lives in Germany, I believe. It's a really nice platform. And the thing that makes it the nicest, the thing that really truly separates it from all the others is its documentation. Truly phenomenal documentation. It's documentation I enjoy reading, which is that's saying something. When you can say, yeah, I legitimately probably sat down and read the entire documentation, and I have never done that for any other library. So it's because I legitimately enjoyed reading the documentation, because it's just so well done. It's so linear in terms of thinking, and its examples put in with it and all that kind of good stuff. So, all right. So, what do we got? So, Fast API is very simple. Basically, that gives you, just like with Express, you can do it in just a few lines. Well, Fast API is the same way. You can import this, and so that's what we'll do. There's our first Fast API server, and let me pip install Fast API. I think. Let me first make sure that we're doing that right. Yeah, pip install Fast API. We also have to pip install Unicorn. This is where Python starts to rear its ugly head with web services. You do need a HTTP runner, or a WSGX or ASGX, in this case a web server, in order to handle concurrent connections, because Python is not inherently a threaded system, and so you need basically a manager of a number of different connections in order to handle that. And so you'll hear things like Unicorn. We're using Uvicorn here, and those types of things. You can read more about that if you're interested. For now, just take it as the Bible of what you need to do in order to run a Python web server. Relatively simple, it's just an extra line. Okay, so we got that. And then if we go to our first steps here, now let's start looking at doing this. So here's this app. Here's one of the really awesome things about Fast API that you guys will like. So I'm going to say the title of this Fast API is Trip Prediction Microservice. Prediction Microservice. Well, not a good day to not be able to type, jeez. And then description is equal to a timing estimator for vehicles. And let's just do a version here. We'll do 0.0.1. Cool. And let's run this thing for the first time. So we're going to, this is where we start use Uvicorn. So we're going to use Uvicorn, and we're going to do a reload, so that we do a hot reload. So whenever we change anything, just like that nodemon, and whenever we change anything, I'm going to do a host of 0.0.0.0. That means I can visit it from outside of just a local host, because remember, I'm in my Docker container. I want to be able to hit it with a browser, so I need to be able to go outside. And then I'll do a port of 9600. That's what we'll say our microservice runs on, because we're not using 9600 right now, because our cloud runs on 9500, right? So we can run 9600 here. And that should work. We just have to run, we have to tell it what to run. And so we have to say main for our app. Why did it not install Uvicorn? Oh, because I spelled it wrong. Jeez. Uvicorn. All right, so it started. So now we should be able to visit it on localhost port 9600. All right, there's our hello world, right? That was our first route. So we defined it app.get. So it looks a lot like Express, right? A little bit different. We're using a decorator here as opposed to an inline function, but And then we're just defining our asynchronous. Now you're seeing some asynchronous programming in Python. That's where this is starting. So that's one thing that really separates Fast API from everything else, is it is inherently asynchronous. And then we're just returning a hello world. But here's the other cool thing. We can say redoc, and it will have automatically generated API docs. So we don't actually have to do all that other stuff with all the middleware and everything. It automatically generates our documentation for us. That's really awesome, right? So that is one really cool thing about Fast API. There is a Node a web server that's a competitor to Express called Fastly, or Fastify. Sorry, Fastly is a company. Fastify. That was made by the same guy who did our microservice, or our MQTT broker library, open source MQTT Mosca, or 80s. And it kind of tries to emulate a lot of the things of Fast API, like auto documentation and all that kind of stuff. It doesn't quite get there, but you can check out Fastify if you want from Node. It looks a little bit like Express, but it's definitely a little more opinionated. All right, so we got this, which is really cool. And so let's actually do this prediction. So instead of this hello world, which is not very fun, let's do a app.put. And we'll do a predict trip time. And we are going, let's just say that we now have a response model equals something. All right. So you might say, all right, so generating documentation is great, but how the hell does it do that? There's no sentience here, right? Does it use machine learning or something? Have they cracked the code of AI, truly AI? No, right? I mean, you still have to tell the computer what your documentation is and what your inputs and outputs to your API are. But we use something called Pydantic for that. Pydantic's a typing system. So remember at the beginning, we kind of described, I might have described, especially in the prep videos, described the difference between a weakly typed language and a strongly typed language. Well, in JavaScript, as you can see, there is no typing, right? You can't, as an example, you can't say, well, this is going to be an integer, right? This variable is an integer. It's just assumed, right? You assign it an integer, it becomes an integer. Python's the exact same way, right? So as you get into bigger teams, and you're developing in larger teams, typing becomes and much larger systems, typing becomes a critical piece of keeping things consistent and bulletproof. And so while languages like Python and JavaScript are great for rapid prototyping, because you don't have to worry about all this typing stuff, which tends to slow you down and it's kind of heavy and verbose, you do run into a time when you do need typing to be able to say, look, this variable needs to be a float. This variable needs to be an integer. And so in JavaScript, there's an extension, a superset language called TypeScript, which you might have seen when you've been Googling around and stuff with all your stuff for Stack Overflow. TypeScript is JavaScript, but kind of on steroids, where you can actually assign types to your JavaScript. We haven't talked about TypeScript through this. Maybe we can talk about it on Tuesday or something if you want. Or maybe next week, let me know if you want to cover it. We can talk about it. But you tend to not include that until you need it. In Python, after Python 3.6, they actually included something in the language, in the syntax, called attribution, which actually allows you to assign types to just in the syntax in Python. They're not enforced, but you can assign types, which we can actually leverage now to do our auto documentation. All right, so one of these things is a response model. But let's, before we do a response model, let's define our input APIs here. Okay, so what we need is we basically need a body, right? So just like we do rec.body, req.body, right, in Express, we need to do this in Python, right, or specifically Fast API. So we're going to define the first argument to our function as body. We're going to give it an attribution. So that's what this colon, this Python syntax is. We're going to call this, we're going to say it's a prediction request. And we're going to make that a type. Now, where do we make that a type? Well, let's create a type. Let's I'm going to create a folder called models. Now models, to hopefully sufficiently confuse you, confuse you all high hell here, models are not optimization models or the things we just built. We're using the same language, we're using the same word model to define our types, right? And specifically our prediction request, which is going to be a JSON body. Specifically, it's going to have humidity, temperature, and it's going to have hour, right? Okay, so we've got this. So we're going to define a models here, and I'm just going to put in here a thing called prediction. And in prediction.py, I am going to import, I'm going to pip install Pydantic. Pydantic is another library that gives you data validation, settings management, and enforces type hits at runtime and things like that. So as an example, you can say ID is equal to int and things like that. So, and really it wraps really well to JSON. And so from Pydantic, we're going to import a base model, Pydantic, and a field. And I'm also going to do some, from built-in Python, some typing. I'm going to import an optional. And that's going to be important for what we want to do. All right, so if we remember what we were doing, we were trying to define what this prediction request. And so we have to do what? Inputs. We need to do temperature, humidity, and hours. So I'm going to do class prediction request. I'm going to extend the base model. So now here's your object-oriented programming for you. And so we're just defining an object. And then what do we need? We need hour of day, and that's going to be an integer. And I'll do this a field. There's some syntax stuff here. I'm going to look this up. But the reason I'm doing this is so I can define and document, but in code here. And so I'm going to say like specified in 24-hour format. Another thing we need is relative humidity. Kind of the same thing, right? Except this is a float. And we got that. And this is specified as a fractional number, right? Like 0 to 1, right? We have temperature, and the temperature is an integer. We don't need the resolution on that. And then this, we just need to document to say it's in centigrade, right? So if I could, geez, type and spell tonight. And then here's where we're going to do this. So this, while we're not going to train for other TAS, traffic area zones, what we are going to do is let's design for the future here. So we're going to say, so we can use the same prediction microservice. We can actually check in, check out models as we need them based on the TAS. So we'll just say for now it's a TAS is an int, and then just for a little bit of realism, we'll just say TAS start position. So this could be a GPS location. Could be, it could just be an entry point, street name, whatever. And we'll just say it's optional for now, since we're not really going to enforce that in our simulation. So we're just assigning types to this stuff. So there's a prediction request. We can import some prediction request from model. Sorry, I'm doing JavaScript. From models.prediction imports prediction request. And then we've imported that. So now, if we start Unicorn again, we should be able to go over here, and we should see now all of our documentation, all just from our typing. So not only are we getting validation for that, we're also getting our documentation. That's a pretty powerful thing if you think about it, especially all the work that we went through with Express. We had to do that kind of all ourselves, right? But with this, we're actually able to define at one place our model, our prediction request model, and it all gives you not only validation but also documentation. So you can kind of see, it gives you examples and see our descriptions there. So that's pretty cool. All right. Okay, so we've got this. Let's actually do the let's do our prediction now. So prediction is equal to predict. And where does predict come from? Well, from model dev dot predict, because if you remember, import predict, because remember we did that here. We actually want to import this. So we're going to import predict here. And what does predict take? Well, it takes humidity. And we need body dot humidity here, or relative humidity. Why is it relative humidity? Because that's what's coming off of our body, right? Our request body. And then we've got hour is equal to body dot, what did we say? Hour of day. And then we have temperature equals to temperature. Well, that's good. So we're able to use all of those. Oops, we need body dot temperature. That's pretty cool. And then what we can potentially do here is we can just say prediction, and the prediction is going to be the severity factor. But here we need to also, right now, if you notice, the response sample, documentation isn't there. So we also have to create a model for our response, right? And so here we're going to go back here. We'll just create a class of prediction response. Extend base model. I'll make it a class. Extend our base model. And we'll just do a severity factor. And we'll make that a float. Right. Go back to main here. We now have to do severity factor. We'll make a prediction. So this JSON object, or this dictionary, which will be converted into JSON, has to match the model of this thing, which it doesn't look the same, right? But really it is, because this is just a class with attributes. It's just key value pairs, right? So we're just mapping this model, which is a key value pair, to our object here. Right, so let's see how that looks. Why did the response not? Oh, because the response model, we need to import it, right? Prediction response. Okay, let's see if that saves. All right. There it is. So we should get something of severity factor back of 0. But let's actually do that. So I'm going to use our trusty postman here. pull this up. All right, so here it is. So we got a put, right? HTTP put, which we've defined here. Localhost 9600, predict trip time, which is just the route here. I'm in my dev container, but that's fine. I'm defining in the body of relative humidity, hour of day temperature in the TAS, which matches our prediction request here, right, and the documentation. These docs. So all I did was put that. If you notice this TAS start position and TAS end position, those are optional, so I don't have to do that. If I do that, I'm going to send. Hey, look at that. We got our predicted thing through a REST API. So we've run our machine learned model and wrapped a REST API around it. If that is not cool, I don't know what is. That is sweet in my mind. I mean, it's like, there's like three things that are truly like adrenaline driving. You know, maybe CQB, probably jumping from an airplane, and basically wrapping a REST API around a machine learned model. Like those three things are like pure adrenaline junkie sort of things for me. I mean, that's just, it doesn't get much better than that. So what you've got here is severity factor. Let's mess with this a little bit. Let's rain. Let's do a 0.3, 6 a.m. and 25. So it's a really nice day. There it is. So that is a prediction if I ever saw one. All right, cool. So we got that. But we're not done yet. Far from done, right? What we actually have to do here is if we think about what is actually necessary, we can do a severity, but we don't know what the ideal condition is, right? What is the severity? Like, what does that mean, right? And if we go back to our the presentation that I was giving, we're also going to need a model in the loop to do that, right? Because that number 0.063 means nothing unless we know what that ideal trip time through that TAS is. And oh, guess what? It's not as easy as just running a bunch of models and then storing them in a table, right? Because, well, every vehicle has a different weight associated with it, different vehicle dynamics associated with it, different conditions associated with it, different timing associated with it, different fuel, different configuration, everything. So it would be unrealistic to take every single input output in every TAS in the United States and try to do it for every single vehicle. Maybe if you only had one vehicle you're worried about, you might be able to do that. Just run a bunch of simulations and get the ideal time for every single one of them, and then just do a map, right? But in our case, you can't, because there's a billion different trillions, quadrillions of different permutations, right? Of combinations. So we're forced to have to actually run that model in the loop when we do that. Now, how do we do that? Well, we could develop a vehicle model here tonight, vehicle dynamics, everything. We could do all that kind of stuff, or we can use the thing we've been using all semester, or all boot camp, and sorry guys, do the use Sumo, right? Because Sumo already has the vehicle model in it. It's actually got consumption stuff in there. And oh, by the way, we can just get some cool stuff like energy consumption, so we can actually turn this thing into an electric vehicle. Let's get what the expected energy consumption is and what the severity for that energy consumption becomes, right? If we have worse traffic. So it's only going to get cooler from here. All right, so what would we have to do? Well, it's a little complicated because now we have to run Sumo in the cloud. And this, so we are I promised you guys, right? We're going to run Sumo in our container. Well, we're going to do it because we don't need the GUI, right? In fact, we don't want the GUI. We want it to run as fast as possible. So I'm going to go into my trip microservice. I'm going to create a new folder, and I'm going to just name it simulation. There's a difference between a model prediction, right, and simulation. So in this, I am going to take my network, right, that we've been using forever. We're going to put these network files into this folder. I just copied them from somewhere else. But this is the same network that we've been using, the same TAS that we've been using since the beginning. If you can envision our Sumo, and I'm sure like Ariv, you've been staring at that thing for an entire boot camp now. You know that network like the back of your hand, right? You know that TAS like the back of your hand. So, and I'm sure the rest of you are like that too. So that's what we're just importing here. And then let's do some let's build a simulation here. So we're actually going to take so we are going to take simulate.py, and we're going to do a few things here. So I'm going to copy and paste some stuff because a lot of this is just coming from our other file. So I'm just taking, so if you know our vehicle.py, right, our embedded domain, I'm just going to take a lot of this stuff because I'm just going to use it. Oh, and as it turns out, here's one of the cool things. Sumo's already installed in your container. You might not have realized that, but Sumo's already installed because we're all using Docker. So Docker, once again, helps us. Might have been painful at the beginning, but it's definitely making life easy now. So Docker's installed, so we can just do that. And then we're going to append the path, the Docker path here. It turns out this is where Tracy is in our Docker container. So we can do ls, and you'll notice that Tracy is actually here in this path here. And then I'm gonna import Tracy. I'm gonna make sure it actually works first. Accept print no Tracy. Okay. And then we make a function called def simulate TAS. And if we were doing this for a production, we of course would have parameters, right? Like which TAS it was, maybe a network configuration file that we want to load in, because you'd have a ton of different network configurations, all that kind of stuff. Well, we're not going to do that tonight but really it's just an extension, right? It's just tedious work at that point. It should be pretty clear how you do that. And then at this point, we have a vehicle ID. And let's just call it simulated vehicle. We don't really actually care what the vehicle ID is, but we need it for Sumo. And then at this point, we're just going to copy and paste from, here, all of this stuff. So we have our Sumo command and binary and stuff like that. Our Sumo binary is not Sumo GUI anymore. It's Sumo, right? So the difference between Sumo GUI, we don't need the GUI, right? Graphical user interface, we don't need that. Just need Sumo. Then we're going to use the path here just to make sure that we get it there. And then we'll just take the route 1, and then I'm going to make, here's a little more stuff that we're doing, which we haven't done yet in Sumo. I'm making a type ID of EV, and I've actually added something in route here of vehicle type, specifically of class of energy, because we want it to be an electric vehicle. So I've just pasted this V-type flag into the network.route.xml file. Unlike fast APIs, Sumo has like the worst documentation ever, so feel free to dig through that because it took me for frickin' ever to figure that out a couple days ago. Very painful, but that's the way to get an electric vehicle in Sumo. Okay, so you got that, and so let's do a few different things. Got velocity. Oops. We want to collect velocity. We want to collect energy consumption because it's an electric vehicle, not a combustion. And then we want sim time because that's actually important. We need to know, that's actually the most important thing we need to know, right? The ideal time. Basically no traffic, just want to know what it's going to take the vehicle to actually go. And then here's our simulation. While true, we're going to copy and paste that tracy.simulate step right here. We only need one vehicle, so we don't have to have all that different logic in there. And then what we can do is sim time is equal to sim time plus 1, so we're just going to add it. The reason we can do that is because Sumo, we know, has a delta t, basically a resolution of 1 second. It goes at 1 hertz. Once a second, it's going to do simulation time. You can change that, but for our purposes, we know it's a second, so we can just keep adding 1 second on. And we know that that's the quasi-real time, or our ideal time, of what we expect the trip in the real world to take. And then at this point, we're just doing a try-catch. So we're going to, everyone know what a try-catch is? You're going to try code, and then if it fails, you can run code in the except. I say try-catch, sorry, it's try-except in Python. Try-catch, in every other language is try-catch. Python is try-except. So speed, we're going to get that from Tracy, just like we do in the other get speed using the Tracy API, and we just need to use the vehicle ID. And then let's get, we're going to append that speed onto our velocity array. So we can use that if we need to. And then energy is equal to tracy.vehicle.get electricity consumption, and then vehicle ID. So that's where we're actually going to get it. As it turns out, I'll paste this in here for you guys. The docs are buried way deep on this, but you can go check this out. In Sumo, there's a bunch of different things on electric vehicle, but let me look at. There it is. Electricity consumption, this, all the way at the bottom, used to access this, and it's in watt hours per second. So we know that from the documentation. So you can get the energy consumption, and we just need to append the energy consumption dot append energy. And then we can integrate that to get the full energy later. And then we need to accept, and we'll just stop it if it breaks. Okay, so we got that.
What is the difference between break and return in this?
Yeah, so if we put a return here, it would, and you failed, it would literally exit this function because you're returning from the function. This break keyword is scoped to only this while loop. So we just want to break, we want to end the while loop, but we want to finish it out. And the reason is because we need to maintain our API contract, specifically the API of this function. Because if we just return, we won't actually return anything. So that's why we're using break here and not return. It's a design choice more than anything. We need to close Tracy so it doesn't fail on us now. And then we need to integrate our energy, because our energy consumption, because we're getting watt hours per second. For the length of our drive cycle, we're going to have watt hours per second, right? So in order to get the full energy consumption, we are going to need to sum up. So full total energy consumed, we're going to use NumPy, and we're going to say sum of energy consumption. And that should give us our total energy consumed. And then we're going to return a dictionary. And we'll return average velocity, because we can do that. So now we can actually do a lot of metrics here. So let's do the mean of this, so velocity. And this is in meters per second, so we got to do 2.2, what is it, 36 something, 9 maybe. And then to convert that to miles per hour, because we're in America. And then velocity, So max velocity, np dot max velocity. Yep. And then we can probably also do, well, we need to do the total energy consumed. And we'll do that. And then what's the most important thing, what we actually want, right, is the time it's taken. So now we just have to do sim time, which is already accounted for up here. And that is our in the loop simulation. So we can do the same thing. We need to test this, of course. So we can do the same kind of thing. So if name is equal to main, so if we only run this file alone and not from another, importing or whatever, we can just run this, and we're going to print simulate TAS. So let's and C space simulation Python. Oops. Put that in the wrong place. Simulate.py. Let's see if it works. So it loads the configuration, and it did not work. Crap. Oh no, it did. We had a problem. Can't concatenate list, not an into list. What the? That is a weird one. Let's do that. Can't concatenate one to a list, right? So we just want to actually add it. So that was my fault. So doing that, there it is. Look at that. Took 39 seconds across the TAS. That was really fast too. A lot faster than our simulation Areve, right? Your 1 minute per step. Well, we did that in probably under a second. Well, we weren't also reporting to the cloud at the same time, so that helps a lot. No socket opening. So what we can do then is we can go back to our thing here, our fast API, and we can get a simulation results. We can say simulate TAS. Go up here, say from simulation.simulate, import simulate TAS. And we got our simulation results, which are going to look like this thing, right? And so what that means is that we can now add a little bit more information to our API. Specifically, let's go back to our model here. So let's add a best case and a worst case object to that. So this is going to be helpful we're already computing it, so we might as well add it, right? It's not that much extra to send that information back and forth. And so, unless you're worried about embedded stuff, which we'll talk about later, but really what it comes down to is we can do a lot of cool different things. So let's do a let's do an object of estimated best case trip data, inherit from base model, and we'll just do average velocity of float. Let's do a max velocity based on just mapping the things that come off of here, right? So max velocity, float again. Let's do a total energy consumed, another float, and let's do trip time, right? Or just time. We'll just do an int. Okay, so we got the estimated best case trip data, and then let's do the worst case trip data. So class of worst case. Is it really the worst case? Not really, but yeah, let's just go with it. trip data. It actually could be worse, but we don't. So we just may not have the data for it, right? But assuming we have the best data, we can say it's the worst case. And then the time is int. All right, so we're going to say of the worst case, we're going to apply the severity factor, right, to what the time is going to be, what the time may be in the worst case, and what the total energy consumed is for that time. We're basically saying the worst case is what our expected predicted trip time is. Not necessarily the worst case, but we could also just change this to predicted trip data. That might actually be better. Predicted trip data. All right, let's go back to main. Oh, we're not done yet though, because we want to only send back. So if we go back here, remember this thing right here was our response to our API. We want to add a prediction, right? And we also want to add the best case as an object. So basically going to say best case is going to be another JSON object. But here's the beauty of these classes. I can just add that as a type. And so basically this, estimated. This is basically just saying that we're going to put these things underneath best case here. And then we'll just say predicted case is equal to predicted trip data. And those are all required. And so in here now, we can go back to main, and we can say best case is going to be equal to simulation results, I think, because it's basically this object that we're getting back, right? And then predicted case. Yep. Predicted case is going to be our total energy consumed. Let's start with the time. So time is going to be our simulation results of time multiplied by our prediction. Why is that, guys? I lost everybody.
This prediction will be giving the severity factor, so we are multiplying it.
Right, except that's not right, actually, right? Because we're actually going to be multiplying this simulation results of time. We're going to be multiplying it by a fraction, which is going to give us a smaller number. What we actually want is to do 1 plus that, right? 1 plus that. All right, so we've got that. Why am I not wrapping? That's really frustrating. Probably because I don't have okay. And then we can do the same thing rather than on this time here. We can do the same thing for our total energy consumed. We'll do total energy consumed. We can actually do the same thing, right? Because we can do simulation results of total energy consumed times R1 plus our prediction. Now, is that actually accurate? If you know anything about electric vehicles or vehicles in general, not really. It's not like it's linear, right? just because your trip is longer doesn't necessarily mean that you're going to consume more energy in the same way, right, as if you were driving. So we're doing some hand waving here, but what I'm saying is you can still do this, right? In fact, we could have done better. It's really simple. It just means we do more with our sumo model, right? We could actually run it then for that worst time. Once we know that prediction, we can actually run it and actually get the real fuel consumption. So we're doing some hand waving here, but let's just pretend like the worst case, that's why we call it really worst case, right? Is really that energy consumption. The absolute worst case is if you actually were to consume on average that severity factor more energy. Way more than you actually would, but yeah, it's cool. So let's just say it works. There's that fudge factor, right? All right, so let's see if this actually works. Looks like it might. I think we're good. Let's run it. Did it work? Oh, look at that. It did work. So we got our severity factor. The best case is basically what came from sumo. Total energy consumed, 54 watt hours. And a time of 41 seconds, which is probably about, 6% worse. Let's do a really bad case. 8. Relative humidity is 1. Temperature -3. 57. Whew, tough. Here's the coolest part to me. It only took 1 second, 1.1 seconds to predict and simulate and get our answer here. Pretty freaking sweet. Right, so let's take a break because now we are going to use this and we're going to incorporate into our embedded domain and our client domain. But 5 minutes. 7 minutes. Come back at 10:30. Any questions while we're standing here?
Now I'm going to take a quick break, but that is really cool. That is just really cool.
That was really cool. We did it all in, what, 2.5 hours?
That's cool. I'm going to be right back. So that was cool, other than the few minutes that I disappeared when my computer crashed.
Nice.
For some reason the battery wasn't charging, and so it just died. Like it completely died. And I tried plugging it in, and it was like, nope, not gonna work. So I at that point just went into the other room, and I'm like, I really was enjoying it. So I was like, ah.
I thought you'd get a kick out of this specific week, Beth Ann.
Oh, this is really cool. No, this is, I mean, I've enjoyed the rest of it, but this is really neat.
Sadly, it is so neat. Sadly, we needed the entire 10 weeks in order to build up to this, as you can see. To really appreciate the full thing of this, and we're not even done with tonight, but to really you do need that background.
Part of what's cool to me is that I do understand the statistics behind it, and I understand the modeling, and I understand the principal component. All of that stuff I do understand. So it's really kind of cool to see it used in this way.
Mm-hmm.
Do you get this stuff, Clayton? Like, do you not do you understand it, but have you used these kinds of statistical modeling? Because you've done a lot of this.
I haven't used those on an application, that type of machine learning. Most of my stuff is really tailored to specific applications, like Purdy tools and that sort of stuff.
You haven't used like LSTMs and like recurrent neural networks and stuff for all the NLP stuff?
No, not even that.
Oh, okay.
I think I've described some of that stuff to you.
Oh yeah, we talked about that before.
Yeah, but it's really language is so bad for this kind of thing. I mean, it's really a garden path, because it makes you think you can do it, and then you get a little ways down it and you realize that it's just not working. So it's
a lot of those models are just computer scientists dabbling in linguistics. In the end.
And a lot of them are based on Chomsky and his ideas about systematicity in language that I think in reality don't exist. It does on the surface, but once you get into it, you realize that there's almost infinite variability.
Yeah.
So do linguists take Chomsky to, people that study linguistics, do they take Chomsky to be, yes, a seminal figure, but kind of a flawed theory?
Depends on where you're from. So the Europeans pretty much think he's a big wanker, and nothing he's done has ever worked. And there's some schools in the U.S. where he's pretty much worshipped. So, I mean, he's been at it for 50 years, and I really don't see anything.
Well, because, English is such a well-defined and consistent language, right? So
yeah.
Obviously that should be.
And it's a model of all other languages, right?
Mm-hmm.
If it works in English, then it works in everything. Right? Yeah. And French, I'm sorry. But, all other languages are, crude and Creoles compared to English and French.
Oh, yeah.
If you're Chomsky. I mean, Chomsky is undergraduate stuff's in computer science. So, I mean, he looks at things as if they were computer languages, and that they were, they're systematic and regular, and they are regular, but they're also variable. They're only regular by habit, not by rule.
Interesting.
Yes, I like that. All right, we back? It looks like everyone's back. All right, so we built our machine learned model. We wrapped it into our own prediction microservice now. Its own REST API. I know there's one API, right? It doesn't even have a database. It's kind of has a database. It has that file, that pickled file that holds our trained regression, our random forest regression in it. So that is kind of a database. As machine learned models grow, that gets a lot more complex, and you'll hear things like data pipelines and things where I do have to store them in databases and things like that, because they, especially neural networks, they're massive. They're terabytes of trained model data, because of the sizes and stuff. They can be. Typically, smaller models are better, and we're seeing. I think finally people are realizing that, and we're starting to train little things. In fact, we even saw that here specifically around this TAS, right? We could have easily built one big old network, right, where a feature was a TAS, and then that feature would just be weighted higher than the others. But we don't want to do that, right? We're much better off training individual little models for all the TASs, and then just pulling in the model as we need it, as opposed to trying to train one big machine learned model that represents all the TASs, because one feature could be a TAS, an integer. So we're starting to see more and more of that realization, which is good, finally. Okay, so so we got that, so that's good. What I've got here is I've booted up my cloud. I've booted up our MQTT broker, and I've booted up our front end. So just the same stuff. I just did it while over break. Stuff that you guys should be very familiar with by now. And so if we pull up our cloud, we've got all of this kind of good stuff. And what we have to do is we have to take this microservice and we have to get our cloud to communicate with this REST API, right? And that's a very interesting thing if you take a step back, because what you're saying is we want our REST API, which is our cloud, to our client and our embedded, to now become a client of another REST API in the cloud. Because we don't necessarily want our embedded device or our front end to necessarily have to hit yet another another backend or another cloud service like this prediction microservice. What is probably the primary reason for that? Anybody?
Security?
Yep, that's what it is. It's all security, right? Because you'd have to build in all the same authorization and everything. And we saw the complexity of that with our MQTT broker, but we had to make that separate. But if we can help it, we don't want to have to do that. Well, the reason we had to do that with the MQTT broker is we needed that as close to the client as possible, close to the edge for speed reasons as possible. For our prediction microservice, we don't really care about that, right? We can actually put this behind our so to speak, firewall of our security, and only maybe do our internal security of the prediction microservice. We're not going to do security on this thing, but typically you'd have keys and stuff, but only from a machine-to-machine perspective. You wouldn't necessarily have to authenticate your clients and users against it. So if we do that, what that means is that we can create a new route in our cloud, right? We're in cloud in index.js. We can just create a new get route. And that get route can be a prediction. Let's talk about the architecture there, though. First, before we go crazy with this. So what we're trying to do is we're trying to broker through from our client and our embedded some prediction. So let's think about what we want. So on the client side, what does the client need with the prediction? We could do a lot of different things. We could predict travel time. We could give estimated travel time, like a Google Maps sort of thing. All those kind of things. Let's just do that. So on our front end, let's just let's bring up our front end here. I think it's 5,000, right? Yeah. I'm already logged in. If we go to our vehicles here, let's just add another another thing here, that when the vehicle starts and goes, it's going to give us a prediction, our predicted travel time, right, in that TAS, in and out of the TAS, just because that's all we have right now. Obviously, you could simulate multiple TASs and stuff, and get a larger prediction and then do more resolution. But sake of argument, let's just do that for it's easy. Everything else would just be a UX conversation, right? User experience and a little bit of pattern stuff based on what we've just done. And then on the embedded side, a little more interesting, but not really. What we can do is we can basically just request the trip travel time before he enters the TAS, so that it knows how to maybe optimally control its power split. Let's say it has like a mixed, a hybrid chemistry pack. It has NCAs and LFPs in the pack. If you guys are battery people. And you might want to be able to know what the optimal split to use those based on the travel time. How's the traffic going to be? And in fact, maybe on the embedded route, we make a special embedded route to give you what the expected velocity profile is, so you can make the optimal decision in order to do your actual power split inside your vehicle, right? So hybrid vehicles, this is really big, right? Things like ECMS, equivalent fuel consumption modeling, stuff like that, and model predictive control, optimal control, things like that. This is what we do in the vehicle, but it's done on board. Now we can actually share with autonomy. We can share a lot of the pre-optimization that we can do in the cloud, push it down to the vehicle, so that we can save money on the computation power that we need on the vehicle, right? Because we can do a lot of it in the cloud. And here's the other thing that's really awesome about machine learning and of what we're doing here is the crowdsourceability. So now we can actually get information from all the vehicles on the street, train against all of them, and then provide all that knowledge that an individual vehicle would never be able to access, right? It wouldn't know like all the history and all this kind of stuff, because in order to hold that in memory, it's way too much. You wouldn't copy the entire history of all your data, right, which could be terabytes, onto a vehicle. That's ridiculous. You wouldn't even do it onto a $50 million airplane, right? Like, that's just not a thing, right? So, but you can communicate with the cloud, which can store 50 terabytes models. And so that's where we start communicating that kind of stuff. So from that perspective, let's do that. So what do we need to make that happen? So the vehicle will just need to get the prediction, more about the energy consumption. And then on the other side, the client side needs to just be able to display a predicted time, right? So relatively straightforward. Well, what we need to do then is we need to basically broker through this prediction microservice here. And we need to do it based on a vehicle. So what do we got to do? Well, we got to do a new get route, which I copy and pasted this from here. So I'm just going to basically use the stuff that's in here. And I'm going to make a new route, and I'm going to call it, I'm going to still do vehicle UID, because it's going to be based on the vehicle. And the reason it's based on the vehicle is because every vehicle is unique, right? Actually, not every vehicle is unique. Every make and model is unique. And so we would have to, if we were truly doing this in a production environment, the make and model, which you get from the database, also has to be provided to our prediction microservice in order to inject those into the Sumo model, so that the vehicle dynamics could be taken into account for the energy consumption. So think about that, as we go. But we got the vehicle UID, and I'll just say predict TAS metrics /TAS ID. Now that's not a very good route name, is it? Not very RESTful. It's not. This is where REST starts to break down. Because what we're doing is we're asking REST, which is very resource convention driven, right? It's all about it's about CRUD resources. Creating, reading, updating, and deleting resources. This isn't a resource. This is a prediction. It's an action. So how do we represent that? Well, if you had maybe a whole thing where you were actually making predictions, you could do vehicles, vehicle UID /predictions / prediction UID, which would represent our trip prediction, slash some of the data that you would need, or something along those lines. For sake of argument, I'm just going to leave it like this. Because we can come up and we can fight all day long. In fact, JC and I fight about this all the time, about purity and REST routes, and we waste a bunch of time just going back and forth about what a route should be and what frickin' route, what HTTP operation we should use on something. But I think we wasted 25 minutes one day arguing on that. But I'm going to leave it like this, mostly just to piss JC off, because he's a bit of a purist, more of a purist than I am. All right, so what we've got here then is we can get the TAS ID, which we're not actually using, but for just to keep it in mind that we're actually simulating for TASs, not for full trips. We are going to do that, and then what we could do is let's do this. All right. We have to import fetch. Now, what is node fetch? If you remember that from our front end, we don't use that yet in our back end. But if you remember in our front end, node fetch hits an HTTP server, right? And so we're going to do this in our cloud HTTP server. We're going to hit another HTTP server, specifically our prediction microservice. So we're going to use fetch there. So let's do that. Let's fetch. And what we have to do is we have to give the URL. And here, I'm going to do something here. Services.config.services.predict. Base URL slash, and then we just have to go to our main.jetpy here, and we need to use this right here. And you might say, what is all this nonsense here? Well, as it turns out, we're doing this so that just remember our deployment and stuff. So I'm pre-optimizing for our deployment because I know we're going to have to do some deployment. So what I'm saying here is, well, I'm going to put this in my config file instead of hard coding localhost. Right, that's all I'm doing. So let's go to our configuration here, pull this up, and what did we do here? We had we said config services predict base URL. So I'm going to create a new object here called services, and just in case we have other microservices like a weather API or something that we might hit later, I'm just going to call this predict service, and then if we go back here, predict, and then we need a base URL. And then base URL, and the base URL is just so that we'll have to do this later. We'll do process.environment. Let's just do prediction base URL, or in this case, we can just say HTTP localhost, right? Port 9600. So now that should work just fine. I'm gonna await this. But this fetch is a put HTTP operation. So we're gonna add that. And so the method is put. We got that from main.py, right? This put right here, which is our prediction microservice. And then we also have a body here. And we just have to, just part of the node fetch API, we need to stringify our JSON. And what do we got? Well, relative humidity. We need to do hour of day. And as I'm typing these guys, where do these come from? How do I know what to do here? Anybody?
It's in the docs.
Yeah, it's in the docs. Specifically, you look at it, it's this thing right here, right? Or it's this stuff for our trick prediction microservice, right? It's just the body. So we got all that. So if we do a get on this vehicle UID, we should be good to go. And let's see, let's do a let prediction results here. And we also have to do that prediction equals prediction dot JSON, and we have to await that. That's just the node. That's the fetch API, right? actually parse the JSON out of that response. And then let's do a let out equals vehicle UID. Oops. So we'll do vehicle UID. So that's a rec.params.vehicle UID, just so that we do that. And then let's also let's add the prediction there. So we're basically just going to pass that through, but we're also going to add a vehicle UID to it, and JSON or res.json out, and send that out. All right, so that's a pretty dumb thing, right? Because we're not really adding much value by just doing that pass through. The only value we're really adding, of course, is security, which is never dumb. But that's some added value. We're going to do something in a little bit to add a lot of value, though, in the gateway. But for now, just hang with me. We're just doing a pass through basically here. We're adding vehicle UID and some security. All right, so let's go to our embedded domain. I've got this pulled up here. This is outside of my container, so we can actually see it a little bit more than usual. And I'm going to oops, I already did that. Okay. No, you saw the answer. It's fine. All right, so if you remember on our stuff, we basically go through here, we log in, we get our tokens and all that kind of good stuff, and then we go through each of the vehicle lists, right? And we add it to the network. Specifically, if you think about it, we're adding it to the TAS. So we're adding it to the network, which is a TAS. So right here on the initial speed, we can also hit the gateway again. Notice I'm calling it a gateway now, not just the cloud. I'm hitting the gateway to then be able to get the prediction. So we'll do a vehicle UID is equal to vehicle of UID. So I'm just going to pull out that UID to make things a little nicer. And then I'm going to say the prediction. We want to be able to predict for the actual request.get, because now it's not a put anymore because we're just getting it from our gateway. We're just doing request.get. So we're going from Python to Node to Python. We're doing a get, and then let's do API base URL. And then we will do vehicles / vehicle UID / predict TAS metrics / what's our TAS number? What's our TAS ID? I'm basically asking someone to come up with a number. Say it's 9. And then, doesn't really matter. And then, it's whatever our TAS ID is, right? And then, we're going to do headers, request headers. We can use the same thing. Remember, the request headers has our security. So that's our value added, right? For going through our gateway, we kind of get that security for free. Request headers. And then we can just say this prediction. What we can say is this vehicle, we can add the prediction to the vehicle object. You just say prediction.json. And then, I didn't do that. So, and then what we can say is print this line: vehicle UID is expected to expend at least the prediction, best case, total energy consumed in kilowatt hours. Pretty sweet. Except it's not kilowatt hours, right? It's in watt hours. So what we got to do is somewhere in our chain, we're going to have to divide by 1,000. Let's see if that still works. Yep, so now it's in kilowatt hours, not watt hours. Cool. When you're coding, you have to have a stream of consciousness, right? You always have to be thinking about all the different stuff, especially when you start talking about this stuff in units. You're going to start to kill you real fast, as you guys know, any kind of simulation or new. Okay, so we got that. Expend at least kilowatt hours. We could have just changed that to watt hours to make it easy, but we don't really think of things in watt hours. We think of things in kilowatt hours, right, for electric vehicles. So we can do that. And let's run it. See if it works. Did that work? Oh yeah, it's working. It just came up on my different screen here. So you can see here that so we got vehicle information, but then there was an issue. What was the issue? Something about a connection closed. See what happened there, guys? Anybody? Incorrect checksum, probably modified after being freed. It's a little bit strange. Okay, so there was something wrong with, so if you notice what I debugged there, I was pretty confident that the previous simulation worked, and it does, right? So I went and commented out what I just did to see if that was the problem. It's usually the first thing you do, right? Go back to what was working and then see. So let's see what the issue is here. This is request.get API base URL. What is API base URL? 9500, that should be fine. Predict TAS metrics, that should be fine. Oh, look at that. I wasn't looking. The reason was, if you check it out, there's actually an error happening in our backend. So there's an unhandled promise rejection. Config is not defined. Oh, that's what it is. So our cloud was actually erroring out. I'm going to squash the broker here. So config is not defined. Well, that's an easy fix, fortunately. Go to the top here. We'll say const config is equal to require configuration. All right, so we're restarting there. Let's see if that works now. Nice. So we're able to, vehicle for that unit is expected to expend at least, 50 watt hours? All predicted from the cloud. It took less than a second to get that information. So then now we can go and compare it, actually what the prediction was, and we're not going to do that because we know it is, because it's the same simulation that's running on a embedded domain in the cloud. But if it was real, it'd be kind of cool to compare that, right? And here's the beauty of it. Reinforcement training. You'll hear these words a lot. So what we can do is now, when a vehicle exits the TAS here, what it can do is it can report back up to the cloud what the actual time was with what its predicted time was. Then we can take that information and what the energy consumed was. We can take that information, add it to a training set, and then retrain our model with new data. And so you have this really cool life cycle that starts to happen and it just gets stronger and stronger from a crowdsourcing perspective. And so that's how you start to get data, right? And that's when you start going from what we call IoT, Internet of Things. If you go back to my initial presentation, kind of intro to this whole thing, where we move from IoT to AOT, analytics of things. And that is what we call operationalization of machine learning. When you're using predictions to feed back through, get that feedback loop back through the system and retrain in real time, and then use those predictions to then continue adding. That's a very dangerous thing, right? And that's why explainable AI is such an important thing in area to research. Things we don't know, right? Especially neural networks. These are black boxes. We cannot explain why they make the choices they make. So you have to be very careful about, if you do that reinforcement training, of being able to assess and think and validate whether or not the data that you're getting you want to actually be training on. And so that's when input and output conditioning becomes a really big thing. In my research, which is using dynamic systems on the input and output of black box models in order to actually verify the validity, right? Whether it's heuristic or dynamic system, physics-based systems, to verify the validity of what you're actually training on and what you're actually getting out. So you're looking at boundary conditions and things like that. So that's really where a lot of the stuff gets really, really cool. All right, so as if it's not cool enough, right?
BJ, for that stuff, is that where, like, does Tesla have a huge advantage in terms of autonomous drive and getting vehicles out and having such a large data set to use for that and for training purposes?
They certainly do, but they're actually no stronger. I think a stronger company would actually probably be Google in that. And the reason is because they have a hell of a lot more data than Tesla. Tesla doesn't actually have that many vehicles on the road, right?
I guess I mean from a pure autonomous drive and on vehicle control.
I see. Yeah, if you're only training on autonomy, yeah, because that's, yeah. I think the bigger question is they do have kind of a head start, but they've somewhat had their hands tied because of what they're actually allowed to do from an autonomy perspective, right? They really are only allowed to do level 3. Now they've kind of pushed the limits of what that means, I think, from a regulatory standpoint into 4 and 5. But they're really only supposed to do it on the highway, and they really only allow you to do it on the highway. And so from that perspective, you kind of get that, but only for a very minimal use case. And basically on the highway, which is one of the easiest ways to predict. You don't need all of this kind of machinery around it, right? You really, you don't, I mean, that's just so easy to predict, right? Because their speeds are fast, there's very little stop and go. And if there is, you're not, from a Tesla perspective, you're not doing autonomous things, right? You might be doing slow and fast kind of things, but not really. So I do think they have an advantage, but I don't think it's like such a massively significant advantage. I think it's Google that actually has the advantage because they have all the Google Maps and stuff of everyone driving. And we will never have, from an autonomy perspective, an ADAS perspective, until we have complete 100% level 5 vehicles on the road and no one driving their own car on the road. A lot of the truly autonomous data is invalid because you always have that chaotic element, and that's grandma driving, right? And so that's what kind of throws everything off from a validity standpoint and I would say reliability standpoint in the safety calculations and everything. But generally, JT, I think you're right. But I think it's more nuanced, and I don't think they have the level of head start that people might think because of those reasons. That's my
gotcha. I guess I was even thinking not even for current usage in a level 3 type situation, but just seeing those types of situations, real world situations, and being able to use that for future development of level 5 type stuff.
Yeah, no, you're definitely true because they do have the computation power on that. But you know who actually has a lot of data and they don't know how to do it are these ride sharing companies. There's one here in Columbus called Share. And what they do is they actually they have no autonomy. You know, they have drivers and everything. But what they do is they have cameras on their vehicles, and they record everything for liability reasons. And the power of recording, and they have like, you know, they have tons of routes all over the city. And so just having that camera data is an amazing advantage. Now they have no clue what to do with it, quite frankly. Don't show any of them this video because I've talked to them before. They have no freaking clue what to do with it. But if they could actually monetize that, that's a very, very rich data set because they're high res images. I've looked at them. They're high res. They are the frame rate is really good comparatively. I think it's like 2 FPS or something. So it's definitely you know, at the point of being able to actually do something with it from a computer vision standpoint and real time standpoint. And they have it all. They've logged it all because it gets dumped every so often after every trip. That's a really valuable data set, and that's not autonomy at all. That's just having stuff. And you know, they oftentimes will show like safety things, not in the context of autonomy, but like, oh, look at how safe our drivers are. You know, they were able to avoid this accident, or they were able to avoid this potential situation of being able to swerve out of the way but maintain control. Which is great to see a human driver doing that, but what that actually allows you to do, combined with CAN data and vehicle data, is be able to correlate from a computer vision standpoint what actually was happening and what the vehicle dynamics of the actual vehicle bus were doing. And that's actually, I think, more valuable in order to emulate that behavior, because humans are always going to be better at making those decisions than a machine is. I think that data is better to be trained on in those situations. And now that we actually have that computer vision, we have all those parameters to actually define what the situation was. I think that's more valuable than Tesla might have from their, you know, vehicles, you know, being able to drive on the highway autonomously.
Yeah, that's kind of what I was thinking about in those, you know, there's a lot of situations that you can think up and dream up. And then next thing you know, you're driving down the highway and you're like, what the heck just happened? And you just responded to it without even thinking about it, right? It's pure reaction.
Yep. Complete.
Whereas you have to train the computer system to do that.
Yep. And what we do now is we have very sophisticated virtual reality and gaming systems that we will actually train our AV computer vision models on, where we will artificially inject. It's like Beth Ann at Windsor, your CAV, right? Where we will artificially inject situations that are problematic. And then we will program. We basically have a video game that someone will react that way, and then get that data, so we'll train on it. Those things are still pretty controlled, right? I mean, it's not an edge case. We might be trying to inject edge case kind of behavior, but it's still not. It's still too controlled. You need organic, natural, safety-oriented things to truly do it. And it's those fleet drivers and things that I think where the wealth of information and where the edge cases are going to happen, and where we need to be focusing to truly get that safety coefficient up. In order to actually put autonomous vehicles level 5 on the vehicle with other human grandmas driving.
Yeah, that'll be an interesting thing to see. But sorry, I completely derail you.
No, that's good. And in fact, there's another boot camp course as part of this kind of program that we put together that's taught by Eric. You guys met Eric on the first call, Eric Reynolds. He does ADAS reliability and verification. And so he has a whole, it's a lot shorter than this. It's a couple weeks long, but it's all about, you know, how do you do verification, reliability, and requirements definition for, and resilience, system resiliency for ADAS, for autonomous vehicles. And so that might be of interest to people who do a mini sales pitch, but to go through that, that's his area, his reliance and resiliency.
Is that part of ISO, just 26262?
Yeah, it is, exactly. So
Okay.
and as part of that, though, he goes really deep into that standard and all that kind of stuff, as well as some of the modeling that they use.
Yep, yeah.
Statistical modeling and things in order to actually do the assessments and all that kind of
Yep. Yeah, the HARAs and all that stuff. Yeah, it's an interesting CYA by the automotives.
It is an exceptionally interesting CYA, but you need it, and there are some good stuff in there, but it is a CYA.
There's a lot of good stuff, but yeah, when you see it, you just go, oh man, that's massive CYA. It's like, hey, we need to all band together. If we do this the same way, we can cover.
Yeah, and that's what it is. It's just too much to cover. So yeah, as long as everyone's doing it the same way, then everyone's fine, right? Herd immunity.
Exactly. Yeah, it really is.
That's a good discussion. All right, so we got to do one more thing. I think we're done with the embedded vehicle. I kind of went off on my soapbox about how we can do reinforcement training and everything. We could be at the bottom here and say, oh, how long did it actually take? You know, all that kind of good stuff. We're going to do that. Let's do it on the front end now. Let's get this prediction, which is practically the same thing. Where did my, oh, there it is. Let's get that one thing here, just so we can say we did the full stack today. All right, so where are we? So we've got that. And all right, good stuff. So we need to go to our front end React. We need to go to our source here. We need to go to our screens. I think we're in vehicles and do this. Okay. So remember our cards here. This is the vehicle screen, and we've got our vehicle card list, and we've been good about doing components. So we're going to go to our vehicle card, because we basically want to do latest data, and underneath latest data, we want to just do estimated time. So we'll just do estimated time from start. And then we're going to have to do an additional get up here. We don't really want to do it in here necessarily. I mean, we could if we wanted to, but it's probably better. Well, yeah, we could do it in there. You want to do it in there? So what I'm debating is we could do it in one of two places. We could do it here, or we could do it actually in the vehicle. I'm actually going to do it here. It's going to be easier based on what this vehicle is. No, I'm gonna do it in the let me think a little bit here, because this is interesting. So we kind of have we have an option, right? We can either do it in the vehicle, in vehicles.js, where we basically have all of the other stuff happening, or we can do it actually in the vehicle card itself for each individual vehicle, because we have to get the prediction for each individual vehicle. So we're going to have to do it one way or another. The big question is, where do we actually want to do it? I think we're going to do it actually in the vehicle itself, and then pass the prediction down as props to the vehicle card. As prediction. So, and the reason I'm going to do that is because I can control what's going to happen a little bit better in terms of like MQTT updates and TAS entry and TAS exit. I can control that a little better, not from the actual vehicle card. So, I do need to do a use effect though. So I got to do react.useEffect, because what we want to do is when this card loads, we're going to do a lot of hand waving here. We're not going to try to like hook it up and try to coordinate with when the vehicle starts and everything, because what we'd have to do there is we'd probably have to get like an MQTT broker topic. The topic would be, hey, trip started or something, at which point that'll trigger us to get the prediction for the TAS and everything. So that I'll leave as an exercise for you guys to think through architecturally how you might do that one on like a TAS entry or that. or something like that? Would you do MQTT? Would you do a REST route? There's a billion different right answers. It's really just what you guys think. So we're going to do some hand waving here. We're just going to assume that we know in the front end that this is the estimated trip time. And I'm going to do a use effect. And for the use effect, I basically did a component mount. And I need to basically do it on vehicle data. So I need to subscribe to vehicle data. So when I get vehicle data, I need to get the prediction, because if you remember what we're doing, what we have here in the cloud is, in order to get this prediction, I need to send the vehicle UID up with it. So I need to get the vehicle data, meaning, and the vehicle UID in order to actually do the prediction. So I'm going to subscribe to the vehicle data here as a dependency, and then I'm just going to do the standard thing here: async function get prediction. And what I'll do here is I'm going to loop through all of these. So I'm going to let v of object.keys of vehicle data, because if you remember, what is vehicle data? Well, vehicle data is an object of all the different vehicles data, right? So, and it's an object with key value pair. The key is going to be the UID. And so what I got to do here is I'm going to loop through each one of them, right? And I'm going to get each one. So I'm going to say let res equals awaits API dot get post. But we need what do we need? We just need a get, so that's good. And then we're going to do a route. JC was nice enough to give us a nice little function for that. So that's that API.get, which just wraps fetch again, right? Just on the front end. And then we got vehicles. And then one of the nice things here is we can do vehicle data of v, which is that key dot vehicle UID / predict TAS metrics / TAS ID 9. We'll hard code it. Where did you get that TAS ID otherwise? Well, you can get it from a map that's stored, or you can get it from maybe a GPS location, and ask what the TAS of a GPS location would be. Maybe do another route or something in your cloud, or hard code it in your vehicle as part of your map. There's not that many. That'd be a pretty easy thing to store, things like that. Okay, so we got the routes, and then what else do we need? Well, the body, we don't need anything. And then we do need some headers, because we need the security. And so we need authorization, and we need the bearer, and we need the token. Where does the token come from? Token comes from the auth context. It's the other reason I'm going to do it in this component as opposed to the other. We'd have to do some more context importation. All right, so we got some use effect there happening now. I need to set some state here, because I need to actually send the prediction down into the vehicle. So what I'm going to do here is say const predictions and then set predictions. So I just have some internal state here. I'm going to use state, and I'm going to do an empty object there. And for every vehicle UID, now in each one of these, I am going to set predictions, taking my previous state, and I'm going to return previous state, and I'm going to say v which is just the UID, the vehicle UID, and I'm gonna just say what res is. So there we go. Now here's the other thing that we have to think about. We have to, from a timing perspective, think about what's happening. Because if we're going to get this prediction, we actually want to get the most recent one, right? And then we know generally that what the trip time is going to be, and so we can say, look, if the time is now, then we probably don't need to get, this is going to be too old to get the estimate, because what it is we can always get a bad time. Like we'll always be able to get an old predicted estimate. But what we don't necessarily want to do that. We only want to get the latest one. So what we can say is we can say, all right, let's do like a let now equals moment.unix timestamp. So that's what the current time is. And what we can say is for here, so if vehicle data of v dot timestamp is greater than now minus 5, so basically if it's greater than 5 seconds ago, or less than, I'm sorry, if the timestamp is greater than 5 seconds ago, then do all of that. Otherwise, we can just say, console.log, too old, right, to get the prediction. It's just that the latest data, we're just checking the data. We're just saying, hey, that data was so old, don't get the prediction for it because it's not worth it, right? Like I don't care anymore. That's 5 seconds ago. We could also make it 30 seconds or a minute or an hour. If it's less than an hour, don't get the prediction because it's old. Like I don't want it. It doesn't mean anything to me, right? So that's going to help a little bit with the realism here. All right. And then what do we got to do? Well, we got to call this function get prediction. And once we get the prediction, we got to go down here and pass this thing down, right? So we need to say prediction. We say predictions of vehicle.uid. So all we're doing is we're passing that down as props, right? So that then we can go into our vehicle card. And now this is on props. We can go down to the thing that we created here, which is estimated time. And we can just say vehicle. We can just say prediction. Props.prediction, if it exists. Well, we know it's going to look like this. So we're just going to say estimated time. Let's just get the predicted case. So we're going to get that. If that exists, predicted case. If that exists, we want the time. And we'll just say seconds. Well, the reason it doesn't have anything is because it's too old. There it is. There's our prediction, 53 seconds. And as soon as this thing comes on, we should see that, right? Because that vehicle. Pretty freaking cool. Now they're all going to be the same prediction, right? Because they're all on the same network, like basically no traffic. So I'll leave it to you guys to play with that, to try to get different things, inject some traffic, stuff like that. It'd be kind of cool. Now there's one more thing that we got to do. This thing is going crazy. For every single time it's getting hit, it's making a prediction. Do we really have to do that? No way. No way. That's ridiculous. There is no reason to constantly do that. You only have to really return it once, right? And in fact, the vehicle is going to request it many times. And in fact, that same route, we know the embedded vehicle has already requested it. We've already done the computation for the prediction and the simulation because the embedded device already did it, right? The exact same thing. So the client, we really don't care about that data, right? That's like a gee whiz, nice to have kind of thing for the UX. There's no reason to use computation time for that, right? So what can we do? Anybody? Anybody?
Most only when the prediction changes.
Well, we know the prediction's probably not going to change in, well, 53 seconds, right? In fact, we know for a fact the prediction won't change in 53 seconds. Because we predict it.
Can't you just put it into a database and call it from a database then?
Yeah, we can cache it, right?
Redis.
And what should we use?
Redis.
We should use Redis, right? It's like a perfect opportunity to use Redis here because it's short-lived, very, very infrequent. It's very frequent, really short-lived. In fact, we know how long it needs to live because we predicted how long it needs to live at the worst case, right? It needs to live at the worst case for this specific thing, 53 seconds. And here's the beauty. With Redis, there's a TTL. And so you can tell Redis only keep this record for a certain amount of time and then drop it. You can set it and forget it then. So you won't even fill up your database at that point. So let's do that. Okay. All right, so we're going to go here. We're going to go to our app.get here. It's really this thing that we want to cache, right? It's the result of this. Well, it's the result of all of this that we want to cache. But in order to know if we need to cache it or not, we need to first check, right? So what are we going to do? Well, we're going to say let p equals await get cache, because if you remember, where does get cache come from? Well, it comes from our database, so lib database here, and we go down here. If you remember, we defined our Redis client, and we defined our get cache, which is just, we just promised-fied our Redis client of .get, right? Set and get keys and values. So we're going to do a get cache, and the get cache is we basically need to pick a key name for the Redis database, right? What should our key name be? Well, it can't conflict with our current Redis, and so we kind of need to namespace it. So the namespace that I'm going to come up with is, I'm going to say predict. So every single one of our predictions is going to have a namespaced predict tag in front of the key. Say predict : and then what I can do is I can do rec.params.vehicleUID. And even cooler, I can do rec.params.tasID. So I can do it by the TAS ID. So I can keep namespacing these things as necessary. For us, it doesn't matter. It's going to be the same TAS ID every time, but whatever, right? All right, so we can get the cache. So we're really looking for P here. And we can say if P exists. So we just say if P. What do? Well, we just return res.json, json.parse P, because we're going to store the output, basically this thing, in Redis. And we don't have to do any of this. It's like the quickest operation you can possibly do. Get the database, go, right? Get from the database, go. All right, well, so we handled the simple case, the case where it existed in the cache first. So we kind of did the inverse, right? Now let's handle the case of actually putting it into the cache. So we know that if this happens, we know for a fact that we'll never have anything in cache because we never put anything in cache. So let's actually put this prediction result in the cache. So we know that if it exists in the cache, it will automatically return here and then stop execution. So it will never reach this. So we're safe to say, okay, if it actually does get in get here, what we can say is we can just do set cache. And what we have to do is we have to take this same key, same key, watch closely what I'm doing. So I use that thing twice now, so I'm going to abstract it. So I'm using cache key, right? And then I need to JSON.stringify my out. Nice, sweet. So that will set the cache. But what I didn't do is I didn't set the TTL on that. And that's because I need another command in Redis that we have not implemented yet. So let's go over to here. We actually need to use setX. And what setX does is it sets the value just like this, but then it expires. It gives a command to expire the key after a certain amount of time. So we're going to need to do a little bit more surgery here to get this thing to work out for us. So we're going to go back to our database file here in lib, where we've defined our all of our stuff, and we're basically going to take this set cache, and we know from our Redis npm library here that all the commands are just Redis commands. So what we can do is we can say, all right, we'll just say setx cache, and we'll promisefy setx as opposed to set. So we're just going to do that, but we know that we can also then take this and go to the next level here in the cloud, and we can just add one more thing here. And what will we add? Well, we want to add the expiration time. What should the expiration time be? I actually said it before.
53 seconds.
Yeah. But I don't want to hard code 53.
So the longest that the simulation takes.
Prediction time.
Prediction time.
Yeah. I want to do this one. Predicted case time, right? Because that's the worst case. That's the longest we would have to save this thing for. So now, if this is real meta, guys, right? Because now what we've done is our predictions, our system predictions, our plant predictions, are now impacting how we're implementing our caching in our backend software system. So they are intimately driving functionality within the software. Right? That is like the coolest thing ever. Our real system is now taking into account, and we're able to actually drive cache times based on machine learned predictions and models from our plant system, from our plant. Like, that is like the coolest thing ever. And that is just sweet in my mind. So what we want to do here is we just want to do prediction. Or predicted case, not best case. That time. This thing's running really slow now. All right, starting up. And do this. And what we can see here. Don't know why this is slowing down. Can you guys hear me? Okay. Oh man, this thing is dragging now. Fortunately, we're right at the end, so I'm not sure why this thing is not quite starting.
I thought this was supposed to speed it up.
Yeah, well, it's supposed to. Oh, well, first of all, that was going to fail. Oh, it will actually speed up the runtime. Just maybe not the development time. All right, we're restarting. I just need this. If I could just get the cloud to start, we'd be good. I don't know why it's not starting. Man, it will not start. Okay. Well, let me see. Let me do something real quick. I'm gonna stop sharing real quick. See if I can free up some resources, and then oh, I think I know what happened. Um, I think Sumo got started way too many times and it wasn't stopped. I let it go too. I get let it go too long, and what it did was it kept creating Sumo processes, and it never stopped. And so I am now in the process of trying to kill some Sumo processes.
So you're in sumo hell.
A little bit. All right. So hopefully that. All right. All right. Am I sharing my screen now? You can still see it.
We can now, yes.
Yeah, this thing will not start up. And short of short of closing my dev container and restarting it, which will take some time to reboot all of the processes up. Oh, there it goes. Let's see here. All right, so it's running now. All right, so recovered. Nice. And then we're going to do Python. There it is. And there it is. But the beauty is, so it'll take a little bit of time to run the predictions, but then after a while, it will start caching these predictions, right? And it won't have to use those anymore. And that's a pretty powerful thing. So I mean, that's a really that's a really good thing. So anyways, that is basically what I wanted to show you this week. Got done a lot faster. We could have done deployment too. Well, I'm not going to do that tonight because that's going to take a little bit longer. But basically, that's let's kind of go kind of in review here. So we built a machine learned model using a random forest to predict trip time using weather, hour of day. We integrated that model into a REST API, specifically a microservice, which we then integrated into our cloud, our backend, by just keeping the same API format. And then what we did was we brokered that through the gateway. We created our backend API into a gateway now. It's kind of a gateway before it because it already had an MQTT broker. But we had that gateway, right? And then we implemented the prediction in order to display it on the front end client, as well as giving it to the vehicle, the embedded vehicle, so that the vehicle could make better optimal control decisions about its energy consumption, knowing what to expect from a traffic perspective. That is really awesome. The only thing we didn't implement but we talked about was the abilities that after it exited that TAS was to actually give its actual time, so that then you could then put it into a training data set and then retrain automatically, which you're just completing that loop, right? That's just pattern. That's more pattern stuff, right? Put more REST routes there, add another route to your prediction microservice to add another, thing to that CSV file or a database now, right? Convert that CSV to a SQL file, MySQL database. Just add a record and say, hey, this is ready to train on. And then pull it every so often, run a cron job every week or something, or count the number of samples. If you have enough observation, retrain them, right? Maybe run some statistics on it to make sure that no one's spoofing your data or it's noisy data or any of that kind of stuff. A little more complexity in that. But at that point, it's just pattern stuff, right? So over the 11 weeks, we have covered an entire front-end, back-end system, mobile app, machine learned model, operationalized AI, basically, all the way through with deployment. Because now all you had to do, you have all the tools you need to deploy that prediction microservice, right? Just wrap it in Docker. It's a Python process. Wrap it in Docker. Put it in there. Put it in your Docker Compose. Once it's in the Docker Compose, push, and it'll auto deploy because it's all CI/CD'd. We did all that in 11 weeks. It's pretty freaking sweet. So you guys should feel pretty accomplished. Now I understand there's a lot of discomfort, right? You guys aren't experts yet. Yeah, it's kind of like, well, I'm still back on like week 6. That's fine. That's cool. It's all here for you. You can keep watching the videos over and over. But that's a lot to go through in 11 weeks. And I think conceptually you guys all got it. Because I've talked to each one of you. I think you guys got it. So now it's just a matter of practicing it. and really, digging through the details, learning the tools, things like that. But you're definitely armed with the knowledge and knowledge and of course the words to search on Google. That's half the battle, right? As you guys know now. So, any questions? No questions. It was a perfect lecture. Nice. That's always good to know.
Too much to digest.
Yeah. What's the question? All right. So, first time in 11 weeks, we actually beat the midnight deadline. Nah, not doing that well. I mean, 17 minutes, but yeah. So, a little bit about next week. So, like I said, next week, no coding. We're done. We're done with coding, unless you guys have questions or whatever. We can do some deployment stuff if you want on Tuesday. We can show how to deploy our machine learn model, but I mean it's just a Docker file. Nothing hard there. And then what we're gonna do on next Thursday is we will basically give you best practices, go over some use cases, do some advanced deployment. So stuff you see in enterprise kind of deployments, Kubernetes, things like that. We'll talk about them. We won't do any examples or anything. They're too much. We'll also go through like some of the AWS GCP consoles so you guys can get a feel for them, especially now that you've done some machine learning. You'll see how these things have actually been platformed as a service. So you actually just hook into them in Google. There's a lot of point and click kind of stuff for this kind of training. And then we'll do some just open discussion about stuff, and then we'll talk about next steps. Next week does not mean that we disappear. Next week is the beginning of kind of the excitement, right? So if you choose to continue kind of developing your skills here, let's pick a project and let's work on it together. Beyond that, and do it at your own pace. We're around, but it's we've invested just as much as or more than you've invested in this, and we want you to be successful, not only for us but for you too. I also generally have a belief that we need more engineers in the world who understand what we just went over, because there's a really, really big lack of people who truly understand the full stack. They're very, very few, very far between. And the more and more people we can educate in this full stack thing, and you just went through, it's possible, the better and faster we're going to be able to develop new technology, which is only going to make things better for us, right? Generally, societally, so and sustainably. So that's kind of the big picture here in my mind. So pick a project. If you can't find a project and you want one, let us know. We got tons of projects. And then let's also have a conversation, because we've got a lot of work to do too with paying clients. So let's have a discussion around that too, what you feel comfortable with, where you feel like you'd be most impactful if you want that, all that kind of good stuff. Moonlighting is also a good thing too. I don't want you to quit your jobs. It's more like, hey, keep learning and all that kind of good stuff too. But we'll talk more about that next week, and what that means for everybody going forward. So cool. Any questions?
So one question, you install Sumo right now into the Docker, right?
Yep.
The same way as we did on the computer. I mean, on a local system. So nothing.
You don't have to install Sumo. It's already there.
Yeah.
And it's already there because of the Docker file.
Yeah.
And we put up the registry, but it's there. You right now, if you booted up your remote container, you type Sumo in it, it would come up.
Okay.
The GUI won't, but it will. And like always, I'll push week 11 code, and you can pull it down and mess with it and play with it. It'll have everything we just did, word for word. Cool. Well, let's call it a night.
Thank you. That was fun.
That's cool.
Thank you. Appreciate it.
Thanks, guys.
Yeah, thank you.
All right.
See you guys.